All right, so it says that we are live.
We are live. All
We
right.
are live. Yes, LRVS 2024. Great, perfect. We're here for this year. Definitely here for this year. And I'm seeing everybody now joining in. I know Ahmed was here from the get-go before time, always early. Good. William Sloan is here as well. We have Greg Livingstone. I know it's early for Greg on his side, so we appreciate you joining us so much and taking the time out to get here. Hi, Ahmed. We're glad that you are here with us. We have everybody now joining in and just coming in, getting your coffee or maybe another drink because it's a different time zone for you. Because we have a lot of different time zones going on today. Martins is joining in. Jed is joining in as well. Like, we have lots of LRVSs across the world, so I know you all will be ready for this. And it is LRVS 2024. It's so this year we're a little bit different. We're trying to make sure that we can reach you all in every possible way. So we figured, why not try a LinkedIn Live? And why not try a YouTube Live? And why not try a StreamYard? Because everybody should be able to access those different things. And it's all about being able to bring the content to you all because we have so many experts in this field and they're just ready to share their content. I mean, we have a great lineup of speakers today. I know, like, definitely great lineup. We have Andre coming in from Canada. We have Hassan coming in from Egypt. We have Mike Johnson coming in from the US. And then, of course, we have Blair joining in from Canada again. Canada seems very popular this morning. And then we have our panel session with Robert Torres, Jim Hannon, and of course, Greg Riddlestone. So it's going to be like a very fun, packed 3 hour session that we're going to be running from now until 12 noon Eastern time. Because I know we have Martins coming in from Nigeria. I appreciate you joining so much because the different time zones, it's like, wow. Yeah, definitely love the fact that you all can join.
This is a global community.
It
I love it.
is
And
all,
MJ said it nicely, right? So many familiar names, and it feels like
yes.
family now. And that's the intent. Yeah.
That's always been the intent because LRVS is a community where we can all come together. We have Saudi Arabia here. I love to hear Saudi Arabia being in the mix as well. So it is a community, and one of the great things about LRVS is that we're always able to meet together and help each other out. And I have a fantastic story about our first set of presenters for the day, and I will get to that when I'm ready to bring them on stage. But that is what LRVS is about, and that's what it stands for in terms of everybody coming together just to share information, to share knowledge. We leave all of the other things on the outside, and this is our safe space to have this community where we can speak freely and share information because that's what it's about. It's really about just sharing information.
There's so much learning to be had. And
Oh yes,
yeah.
get your notepad ready. I have mine.
Yeah, just a couple minutes, right? So this is going to be recorded. So if you have to top up your coffee and you miss a session,
Yes,
you could always come back and see the
definitely.
materials. Yeah.
Yeah. So I'm gonna get Hassan and Andre ready because I know you all are excited about them joining this morning. So one of the great things with Hassan and Andre is that they actually met during LRVS and they had a beautiful project that they were starting to work on. And they were like, we need to pitch this to LRVS 2024 because it's because of LRVS that they were able to go on this project. And they wanted to share some more information on that. So I'm going to bring them on stage and right now because, they are ready. Of course, they're ready. And what they're going to be talking to us this
Yep.
morning about, oh boy, yes, you all are. So We have Andre with us and we have Hassan with us, and they're going to be taking us through building a PF curve. Now, PF curves and I have a very strange relationship, but I'm going to leave that right there. Um, this is actually to get, it's an example that they're going to be doing within the industry and something that they worked on because after LRVS last year, they were like, oh yeah, we definitely need to get this going. And I love the fact that we were able to bring together Canada and Egypt for this presentation. So I'm going to hand it over to the very capable hands of Andrea and Hassan, and they will be giving you some more information on what they got done. So we'll see you all in a bit. Off to
Okay.
you.
Okay, so over to me. Thank you very much, Sanya. So, hello, LRVS 2024 America, Maintenance and Reliability Community, and everyone attending. My name is Andre Michel Ferrari. Thanks again to LRVS for having me again this year. Wow, time flies. This is my third year presenting and fourth year attending LRVS. And so also a special thank you to my colleague Hassan Abdel Nabi, who is the co-author of this study and co-presenter today. Hassan and I, as it was said before, met on LRVS 2023, and we decided to work together in order to share learnings to the community. Well, this exactly means, as Sanya said, that LRVS brings the community together. So it's not only a great learning forum, but a fantastic incubator of collaboration. So you'll see that today because we're going to talk about the PF curve. Hassan and I built one using real industry records. So it's not just theory, it's the real thing. So anyway, fasten your seatbelts and here we go. So this slide's about the authors and their pedigrees. You're welcome to go through it and know more about them. So in this study, Hassan wears the maintenance engineering hat, and I wear the reliability engineering hat. So moving on, today we'll talk about what the PF curve is about and how we gather records or data to build one. We will build it and then highlight the information it provides. We have enough records to build this PF curve, but we find, you'll see later on, that we can do other stuff with those records. Finally, Hassan will give us a practical overview of what this study can provide to the maintenance department. Moving on. In my past career, I've heard a lot about PF curves, mentioning here and there, but I never saw how one was constructed. Uh, I really like to know what's under the hood before I drive a car. So the PF curve is essentially a graph showing specific points corresponding to the health deterioration of a component over its lifetime. It represents the normal process of aging, like for us humans, we age over time, our health deteriorates, and there are specific indications of deterioration that we can find over time. Have you ever heard a doctor saying, based on their diagnostic, this particular patient has 5 years left to live? This is essentially what a PF curve does based on a specific diagnosis criteria. For example, a vibration spike. And then we can estimate the life before a failure occurs. So in a PF curve, the P stands for potential failure. For example, the bearing is vibrating but still running, but it might fail in the future. F stands for complete failure. The bearing has failed and it cannot perform its intended function anymore. The interval between the P and the F uh, is the time we use to plan for mitigation or repairs. The PF curve is essentially built using condition-based monitoring records and failure records. The more resources we have, the more condition-based diagnostics we can perform. Therefore, the more P points we get, as shown on the bottom graph, the more PF intervals we will get. So in this study, for simplicity purposes, we will define only one point and one PF interval. I will now pass on to Hassan, and he will talk about the equipment we studied and the data points we used to get the PF curve. Over
Thanks,
to you.
Andre. Thanks, Andre. Hello, everyone. Before I start, I just want to say that I'm happy to be part of this amazing event once again. So we decided to work with our tissue mill. It's a huge and complex machine. It has three sections. Okay, the wire section, the F part is responsible to form the tissue sheet paper, and the B section is responsible to transfer this sheet to the drying section in the Yankee section, and the last section is the Yankee section. This section is responsible for drying the sheet. In order to make the study as simple as possible, to help us show you how we can build the PF curve, we selected 11 rolls which has identical bearings in type and size. In this study, we will focus only on the bearing defect. So next slide, please. In our study, we started the machine. The mill started in 2008. So we tried to gather a reliable and valid data. So we used our data from SAP system, which was implemented in our factory in 2015. We also used the maintenance log in order to get the F point, the fail port, and we used the vibration analysis program in order to come out with 7 vibration records that it is used to generate the B point. We only used 4 points because they are considered at or above our acceptable threshold. As for the vibration threshold, we are guided by ISO 10816, currently 20816, and we will talk a little bit more in the next slide. Next slide, please. So, vibration analysis of the bearing. So the bearing has 4 stages. For us, stage 1 and 2 are very difficult to see actual damage on the bearing. It's all about subsurface crack. We only consider these 2 stages in order to make sure that the bearing already available on our store, or we are on our progress in order to purchase the bearing. We are focused on stage 3. So stage 3, you can see an actual damage on the bearing, and also you need to remove it before it reaches stage 4, because stage 4, the behavior of the bearing itself can be unpredictable and it can fail anytime. Every stage has its own symptoms, and we follow all of that, and also we monitor the vibration amount, the vibration level in order to make sure that it does not exceed the acceptable level of the ISO. So next slide. So vibration analysis of the bearing. So it is a complex process, but I want to make it as short as possible. We monitor the vibration parameters, so acceleration, velocity, or displacement, and see if there is any change in these values. So where industry know, in fact, is that if it increased 20%, you need to look at it in more depth and details. So if it increases, we look at the spectrum analysis and time wave analysis in order to make sure that we find the symptom of the bearing defect. All of that can help us to build up the baseline and set up the alarm level, which can help us reduce the amount of analysis. And also, if we are in doubt, we compare these values with another similar equipment. All of this are done in order to make sure that when we say the bearing need to be changed, we are giving the actual judgment. After all, condition monitoring, vibration analysis is a condition monitoring technique. So we monitor the condition all the time. So next slide. So this is an actual image for the software we have, but this is an shock pulse technique. So it is another technique that we use in order to give us a pre-warning even before vibration. As you can see, that we can detect the bearing failure, and also we can monitor the value of this change in amount of vibration. We use SPM in order to give us a pre-warning. Maybe a bearing has a long lead time, and we need to start working on it even more than the normal BF curve. So back to you, Andre, to start our reliability study.
Okay, thank you, Hassan. Thank you very much. Let's move on into the reliability study we conducted. So the PF curve will be built for the population of identical SKF bearings Hassan mentioned earlier. First of all, let's look at the reliability analysis process we use. So we get CBM and failure records and calculate the time to failure for each of them. The first graph on the left there. Because all the time variables are random, they are best represented by a statistical distribution in the graph in the middle. So we demonstrate that they follow a Weibull distribution. And once we have defined this distribution in the middle, we can do various calculations. I put an example here, such as probability of failure in this case. So this process will eventually provide us with the PNF points for the PF curve. So the assumptions are all listed below. Assumptions are important to ensure that the study is rigorous and well conducted. So moving on, using this process highlighted earlier, we have literally modeled how a typical SKF bearing in our sample is expected to deteriorate or fail over its lifetime. This slide represents the probability of achieving each point after a specific time interval. So we have two sets of data, P and F. So we have two models shown in this slide. So we have highlighted in the little box there in each graph the Weibull distribution parameters eta and beta, which characterize the distributions for each category. So those parameters are crucial and unique to the model and will help us define the PF point. Moving on. So finally, here we are. We are ready to build a PF curve. So we use the scale parameter or eta value, which we obtained earlier. This parameter corresponds to the expected time to see a specific condition of failure. Therefore, the expected time to see the first P point, or the point where the high vibration threshold is reached, is around 57 months after the new bearing is installed. The expected time to see the failure point, the F point, is around 88 months after the bearing is installed. So the difference between those 2 points is, as shown on the graph, is 31 months or 2.6 years. And this value, 31 months or 2.6 years, is your PF interval. Moving on. So now let's see how we can interpret the results in a practical way. What does this mean for the person like Hassan who's going to operate and maintain the equipment? What we get from this study is a PF interval. We did not really focus on the vertical axis, which is the health of the equipment. We focus more on the horizontal part, which is essentially the elapsed time or lifetime. We now know that if we hit the P point, we have 31 months to do something about it before the bearing fails. So in other words, at the P point, the bearing is still functioning, but it is in a degraded state. Nothing has failed. However, we do not want to get to the F point where the machine fails, because if the machine fails, we lose production and revenue. And in extreme cases, it could be catastrophic with secondary damage. Or the failure could put worker safety at risk. Safety is a value and very important in industry. So therefore, we have 31 months to prevent a failure and plan a repair accordingly. Just on a side note, in our case, we have limited records, so the model precision is low. For example, for the P point, we use only 4 data points, which is very low. So our confidence boundaries are large. The model is not that precise. We still want to use the model as it's better than having no model at all. But maybe we want to be conservative or careful. In order to be conservative, we use the lower confidence bounds. It provides us with the lowest PF interval, which is 15 months or 1.3 years. This is half of the initial value, and that's why it's conservative. More data is always good, so we want to update our model as we get more data points. We will then have a better model with narrower confidence boundaries. We can also ask ourselves if we are satisfied with such a long PF interval. We can plan the change of a bearing in a much shorter interval maybe. In this case, as shown on the bottom graph with the blue background, We can choose to implement another CBM test, such as lubrication, and define a shorter PF interval. So, for example, if we choose lubrication, we would have the same approach as vibration. This is find a threshold within our lubricant test results. For example, the appearance of a metallic contaminant that indicates impending degradation. So once we have defined this threshold, we would need to gather all the records and timestamps of those threshold occurrence after each bearing installed. The rest is exactly the same. It's exactly the same. The F point stays the same unless we have new data about failures and we can refine our model. So moving on, going a little bit, it's a busy slide. I'm sorry. Let's look a little bit further in the analysis. We did all this work. We have all those records. We crunched. We got only one value, which is the PF interval. Can we get more from the analysis? The answer is yes. But now we have to throw in another variable, which is cost. That is money spent doing maintenance or inspections. This slide shows the use of the optimization tool. I will briefly go through it. There are lots of details on the slide. I apologize for that. So if you need more information on how this is done, you're very welcome to contact me. So in the Egyptian context in Hassan's factory, if there was an unexpected bearing failure, it would bring down the mill at a cost of, on the left hand side here, at a cost of 13,000 US dollars, mainly in terms of revenue loss. If Hassan planned the replacement rather than going towards an unplanned replacement, if the planned replacement would cost him only 2,000 US dollars. Hassan does vibration inspection monthly at a cost of one US dollar per bearing per vibration check. So he does it monthly at a cost of $1. So this is low according to North American standard, but this is what it is. And then we move all this information into the optimization tool, and we find that it's cheaper to inspect the bearings every 2 months rather than every 1 month, as Hassan is currently doing. If he inspects every 2 months and he finds that the threshold has been met, he has 31 months or 15 months to be conservative to change the bearings. He also has a choice to do a planned replacement every 43 months, sorry, it's on the right hand side here, with no inspection. But it is more expensive, sorry, to do a planned replacement than having an inspection strategy. Finally, in terms of cost benefit, if Hassan inspects his bearings every 2 months rather than every 1 month using vibration analysis, his cost benefit is 31 US dollar cents, 0.31 US dollars per bearing per inspection. And when you add all the 22 bearings together over a year, it comes to 6.82 US dollars. It's a very low number, but this is what the model suggests. So if I take the same concept and look at this methodology again in the context of North America, where prices and costs tend to be higher than Egypt, using the same life statistics, we would have an increase. For example, we have an increase in unplanned failure costs from $13,000 to $25,000. We would have an increase in repair costs to $2,500. And the cost of doing one vibration inspection is significantly higher, from $1 to $50 per bearing. As before, it turned out that it's cheaper to inspect. When we run it through the optimization tool, we find it's cheaper to inspect and replace the bearing if the vibration has been met, rather than doing a planned replacement. The suggested inspection interval is every 5 months, and so we inspect every 5 months, and if we hit the degradation threshold, we have the PF interval time to mitigate. So if we use the 5 monthly inspection strategy as suggested here, our yearly savings compared to doing monthly inspection goes up to it goes to will be saving $792 per year. So Just to conclude here, um, our PF curve now comes a bit like a Christmas tree where we adding decorations to it based on the optimized calculations we did on the previous slides. We now add the recommended inspection schedules, by taking the same data we use to build a PF curve and adding some cost information to it, we are able to refine our maintenance strategy. So I've talked a lot now, but before I pass the microphone back to Hassan, I'd just like to make some concluding remarks on the reliability study. So as shown earlier, the PF curve provides good information, but it's limited to the PF interval. So it would be great to take the same records, all the records we used to do the PF curve, and add the cost information to it in order to get an improved maintenance strategy, as we showed earlier. Just a little teaser here with the information we have. We can even go further and build a reliability block diagram, but that's another presentation for the future. But it shows you how reliability engineering can be versatile, beneficial, and fun. We had lots of fun with Hassan. So having said that, over to you, Hassan, and thank you so much, Hassan, for working with me on this case study.
Thanks, Andre. So, maintenance engineering review. So, first of all, you need to monitor your performance. You need to keep record of failure times and mean time between failure, mean time to repair, machine availability. All of that, you need to analyze your performance in order to find the improvement point in your department. So, we were able to build our case study because the availability of data. If we don't have data, we will not have nothing. We will have nothing, and we will not be able to build anything. So, if you are not keeping record of your maintenance log now, start now. And if you want to find the correct KPIs that you need to monitor, you can ask your peers in the industry because every industry has its own KPIs. Of course, you can come to the consultants and can help you to build your KPIs, but you need to monitor your performance. As for the BF curve, our conservative approach was 15 months. So 15 months for me as a maintenance engineer is important to have the time to plan the task. You need the time to determine the spare part needed and it's available or not. You need to locate the resources and the manpower needed to perform this task. So from my point of view, having a big or long BF interval is essential for you to have a correct behavior in your maintenance because you want to perform all of that under the safety umbrella. So if you have more time, you will have better time to plan and you have a good result at the end of the day. Which brings us to the last remark on this slide. So CPM or preventive. From my point of view, if you selected the optimal condition monitoring techniques that fit your failure type, you will save a lot of money and time more than looking at the preventive way. Because if you follow only the OEM general guidelines, you will end up by changing bearings or changing spare parts that does not need changing depending on your situation. Following condition monitoring techniques like vibration, ultrasound, or any other condition monitoring techniques can help you save a lot of time and money. So next slide, please, Andre. So this is our final slide. So I just want to say, if you want to start, there is an easy way to start your journey in reliability. It can begin by creating your critical asset list, and then you can look for bad actors, equipment that cost you most pain in cost or downtime. If you integrate both of them, you will find the critical assets that needs your attention. You need to work on these assets in order to decrease your downtime of the whole plant, not only the critical assets itself. If you selected the optimum CPM tool for these assets and you find a suitable way to maintain it, you will end up by increasing the performance of your assets. So you need to analyze this performance and you need to analyze your maintenance activity performance. But at the end of the day, you need to learn from your mistakes, you need to adjust it. And also, if you are working okay and you can see that your results are fulfilling your KPIs, you need to make it as a standard way to work with in the whole plant, not only the critical assets. So finally, I just want to thank Andre. It was a pleasure to work with you, my friend, and I hope we continue working together.
Yeah, so thank you, Hassan.
Thank you both, Hassan and Andre, for that awesome presentation on the PF curve. And I just want to make sure we've got some time for questions. And Andre, we've got Med, who's asking which condition-based monitoring tests do you prefer between, I guess, vibration and lubrication or others? And then what's the cost difference between them?
So
That's an excellent question. I guess it was for me, but then I was gonna pass it on to Hassan because uh, I uh, I'm the reliability engineer. I just get information or data, and what I prefer might be relevant. I think it's more about how much it costs the maintenance engineer to maybe implement different types of condition-based monitoring. So, and the feasibility and the economics of doing it. But whatever works, I would usually liaise with the maintenance engineer, and whatever he can afford, whatever the company can afford, and also it's about whatever is most economical. Then we try and use it. But I'll pass on this is great question to Hassan. Which one do you prefer, Hassan?
okay, every failure pattern has its optimum condition monitoring techniques. So if you want to monitor rotating equipment, I would say that vibration analysis can give you an early warning and cost-effective analysis, cost-effective solution to find the P point early as possible. Because in Egypt, lubrication analysis maybe costs 10 times more the normal vibration analysis. So from my point of view, it all depends on what the failure pattern you are seeking to understand. This, if you create your own failure mode and effect analysis, you will find out that using an integration of vibration and lubrication will give you an optimal results and confirms the results. Confirming the results is everything you need at the end of the day to say that this bearing is damaged and we need to remove it. No one to remove the bearing and find that there is still life going with the bearing and you made the wrong decision. So combining both of them can give you the best result. But from my point of view, for rotating equipment, vibration is the best way to understand if there is a bearing defect that it is related to the movement. But if you are seeking to know that if there is a contamination or something like that, if you select the optimum point to take your oil sample, you can get it's even warning, the pre-warning even before vibration, because it starts to wear out before to vibrate. So if you selected the optimum point, you will find out that at the end of the day, you know it's we are all every time we are seeking that we need to know as early as possible the viewpoint. This is what I have in that.
Thanks, Hassan. And Vonda says, well said as well. And I think we're wrapping up on time, but wanted to share a few good comments out there. So Terry happily stumbled upon this on LinkedIn. So thanks, Terry, for joining us, and glad this was good. And I think we have one more quick question from Kaved here, who's do you accept 57 months as a normal mean time between failure for that bearing, especially when you take 22 different bearings into account? So quick answer on this one.
Sorry, what is the question? I beg your pardon.
Do you accept 57 months as a normal mean time between failure for that bearing, especially when you take 22 different bearings into account?
This is the expected life to get to the P point. It depends. It depends on the bearing. It depends on the condition that the bearing's working in. I mean, with Hassan, we said that this was acceptable. It made sense to him. This is an excellent question because So I always say I'm dumb. I'm just working with numbers that are given to me. But the way I validate those numbers, I go back to people like Hassan and say, "Hey, I got this number. Does it make sense to you?" So he will say yay or nay. But in this case, the number that we got made sense to him within the environment he was working in. So then once it makes sense, if it didn't make sense, maybe we had issues with data. We didn't have enough data. There were data points missing. But in this case, it made sense. So
Okay, I want to comment on that before we end up. So, from my experience, so the bearing expected lifetime according to SKF is like 5 years with 60 months. But you need to make in your consideration the lubrication, the load, the temperature, and everything. That's why we said in our study that we took the conservative approach, even 15 months, because at the end of the day, mean time between failure is actually what is going to be done, but we are seeking out the B and F interval. We need it to be as long as possible in order to plan yourself. So 60 months or 75 months is acceptable in the industry for 5 years to have the bearing to be filled. But I have bearing here more than 5 years, and it was expected to fail after 5 years. If you create a good environment for the bearing,
and that's why there's randomness in the records. Oh, just
you
going
need
back,
the
it just
bearing to
came
last
back to me that
Hey
as
guys,
much as possible.
sorry.
I want to hear this, and I know everybody, but we're right on time. Thank you so much for sharing your knowledge. This was excellent, and you guys can when we take you off here, you can make comments. The people who are asking more questions, and you can answer
Yeah.
them in the chat. All right, thank you all very much.
Thank you.
And
Thank you so
Thank
much.
you.
be ready
It was a
for
pleasure.
next
Thank you.
next session starting in 4 minutes.
All right. Let's see if we get Mike Johnson on screen. Yes, definitely. We've got you here. Can you help me and try to do your presentation, share your presentation with us? Because we'll be getting ready to go in a little bit. So if you go to present down below, and then it goes straight to your screen. Because we had a really good session just now with Andrea and Hassan, of course, because they gave a lot of data. You know, my feelings on the PF curve are always very mixed. You know, I love it, but you know, it's that Christmas tree at the end and trying to figure out the right points. So I love that they gave so much information on, you know, being able to get that PF curve sorted and how they can do that. Because a lot of times that's one of the areas that a lot of reliability engineers have trouble with. So I'm glad they cleared up a lot of that information. And I definitely, you know, I have a preference for the lubrication side of things. So, you know, when they ask the question about vibration versus lubrication, you know, I have a little bit of preference, but that's just me personally. We can do both. When you do both, it definitely helps. So I think if we get down to the bottom of the screen, there's a present button straight down to the bottom of the screen. And when you click present, it should help you to share your screen. If that helps at all.
Okay.
Yeah, we will try that.
Screen,
Yeah.
entire
Oh,
screen. Here we go.
yes. Let me see.
All
I'll see if
right.
it comes up.
The share screen is still grayed out, but the share button is grayed out.
Ah.
Entire screen.
Mhm.
Okay. And now I can see that. There we go. Here we go. Right. What do you know? Magic.
You got it. And let's go to your presentation.
Okay.
So I'm gonna add this to the stage, and we will be getting ready to go. Because I know everybody's excited to have you here, Mike. Everybody wants to hear about this cost center, moving from a cost center to a competitive advantage. Because I think that's one of the things that we always hear about within this sector. They think that everything is a cost center. Everything is a lot of you know, they have to prove this to the budgets, they have to prove this to finance. So I'm gonna give it over to you because you are the expert here,
Thank
and
you.
you will be helping us to find out on how to, you know, move it from a cost center to a competitive advantage.
Can you
So
hear me all right?
yeah,
Very good.
you're all good to go, Mike.
All right. Thank you for the opportunity to visit. And I'm trying to page forward on my, here we go.
Ah, yes.
A little bit of information about me. This can be provided to you after the fact if you like. A little bit of information about the various things we do here. We focus on mechanical reliability improvement through everything related to machine lubrication, except selling lubricants. We don't do that. Why is machine lubrication considered a pathway to improve financial stability? We've been told by the people that study our bearings in the dynamic film that supports the bearings, that floats the elements in the races, that our industrial world floats on a 10 micron film of oil. The better our research gets, the more we see that we're not quite so lucky. The reality is we're floating our element bearings on a 1 micron, well, 0.5 to 1.5 micron, and our journal bearings on a 3 to 10 micron thick oil film. Now, on the one hand, that's extraordinary that works, and it does work. On the other hand, realize that we're trying to live our industrial livelihood on an oil film the thickness of a red blood cell. It's a precariously thin layer of protection. We recognize with our day in, day out activities that we have to do whatever's necessary to sustain that red blood cell thick layer of protection in order to protect productive capacity. If we lose our oil film, all of the effort we put into installation, alignment, and balance is lost. It's gone. So our day in, day out activities should be focused on doing whatever's necessary to preserve that precious oil film. When we lose that film, we suffer wear from surfaces rubbing, wear from contamination, wear debris and atmospheric contamination. Contamination leads to fatigue, suffer wear from corrosion, and all of those things generate lost productive time. And it doesn't really matter whether our repair activities are scheduled or unscheduled. Once time is gone, it's gone. We lose machine repeatability, which impacts product quality. We have increased risk of injury. We have a higher cost of production per unit, whatever it might be, all of which contributes to lost competitive position for our company, for our enterprise. The people that supply our machine parts recognize and actually support doing things that are above and beyond the perceived call of duty to protect our bearings and our other lubricated machine parts. Here's a slide from SKF data showing the proportion of lubrication-related factors leading to premature bearing failure. Schaeffler FAG bearing says, yeah, that's close, but actually it's not 57%, it's 80% of contribution premature failures comes from defects with our lubrication plan. These defects are all measurable, predictable, and avoidable. So what? With all the things that you have to do, why would you bother investing more effort, more money, more time into trying to address something you're already doing, but address it more effectively? Well, time is money. You all have all heard that, I'm sure. What can you expect from deploying a more precise lubrication work plan, precise product selection, precise quantity, precise volume, precise contamination control, precise location? What we would expect to occur would be reduction in replacement of lubricated machine parts. A reasonable target is 25% reduction. An ambitious target would be 50% in the frequency of repairs over a 3-year period. Elimination of labor associated with those repairs, any contract labor associated with those repairs, and far and away, more importantly, increased net production output. Regardless of the cost it is incurred to replace machine parts, that dollar value pales in comparison to the potential of increasing production output without adding new production machinery. There's various different ways companies go about measuring success when making improvements. Here's a kind of complex chart, but it shows the deployment of a contamination control, a key element of machine lubrication, over a multi-year period that concurrent with increased fluid cleanliness, obviously, that's expected, but also increased output liters per second, part of a design plan. Here's a similar chart showing an 8-year progression in pump replacement decline following implementation of contamination control. Another steel mill in Japan showing very similar results over a 5-year period. A major paper mill where they actually got into the hard cold numbers showing that the deployment of precision lubrication program, storage and handling improvements, training, contamination control, and the implementation of the program itself over a 5-year period, with 2015 being year 1. And regardless of what this very large mill spent, the key point is here, the estimated return on investment from their metrics, from their operation, $500,000 spend and $8 million savings, a 1,553% return on investment. I've done multiple cost analyses during benchmarking sessions at multiple facilities, and these numbers, the ROI and the estimated savings over progressive year, net present value, if you will, always turn out to be larger than expected. And that is because our machinery, our livelihood, floats on an oil film that's the thickness of a red blood cell. Anything that we can do to improve the effectiveness of that machine-saving film produces huge returns in terms of productivity and reduced cost. There's a safety improvement element as well. Overall equipment effectiveness, asset utility measure over a 5-year period. This company showed as their injury rate increased as their asset utility decreased. It's a large French chemical company, a pretty healthy study showing a tangible safety benefit, even showing correlations and risk injury to PDM type work orders versus corrective work orders. There's a lot of reasons that we should focus on doing whatever we can do to tune our lubrication program up to achieve the best possible outcome. Right product, right volume, right frequency, right product, right volume, right frequency, right location, and the right attitude. As it is today, as you look on at this presentation, your system, whatever you have in place, is perfectly designed to give you the results that you are enjoying or not enjoying today. If you want different results, you have to have a different system. So let's think about the system and how we go about achieving improvement in this system. There's 5 key steps that we would identify as systematic improvement steps. It starts with a hard, cold, objective measure of the current state of affairs such as they are today. We often find when doing these benchmarks that customers lack the detail that they believe they need and want to have for their lubrication program, improvement in lubrication program activity. So let's focus on that piece. Few challenges that need to be met when you dig into the many details associated with machine lubrication. Reliability centered lubrication is detail intensive, so you have to have a plan to organize and manage the details. Secondly, we have come accustomed to leaning heavily on our lubricant providers to tell us what the right answers ought to be. Now, lubricant providers' job is to sell products. Having come from that world many years ago, there's constant pressure to sell another product. That plan focuses on more lubricants in your plant site, where your plan should be a focus on machine reliability, starting with your most critical assets and focusing on those areas that have the most vigorous challenge to operations. What kind of details do we need to consider? Well, labor is a very important part. We need to have a thorough understanding of what our weekly labor requirement is going to be, such that we can plan our annual labor requirements. And it's not difficult to do this, but it does take having the right details in hand. You consider a critical process pump. We've got to have a plan for the motor bearing lubrication, drive side, non-drive side, a separate plan for the coupling, if there is a lubricated coupling, a separate plan for the driven machine part. Each component requires a plan, and the plan must be organized such that the work can be executed efficiently. And we do have software tools, plenty of them, that will give us the means to do that. When considering a critical pump, we need to have a plan that tells us how much labor will be required for that one pump. And then if we got 1,000 pumps, we multiply that annual plan by 1,000 to account for that particular machine type. So we have 4 visits typically to lubricate the motor over the year, 2 visits to address the coupling, 52 visits for a level check, unless we're using automation to control levels. Maybe if it's an important enough pump and we're doing sampling, maybe 4 visits to do samples and 1 visit hypothetically to do an oil change. We could conceivably measure 63 visits by a technician. We need to timestamp each one of these tasks, multiply out the timestamp per task by the number of visits to give us an annual requirement for that pump. And the same with other machine types. A direct coupled fan, for instance, running the same exercise, we may find 30 visits. Based upon the size of the bearing supporting the shaft and the speed that it's turning, this may be more, this may be less. A critical conveyor, a lot more parts to attend to and a lot more tasks or visits to each component to address the things that must be addressed to float the component's parts. So we line up all of the tasks. We see that even a relatively small production site produces a very large number of tasks. Now, we're pretty good at keeping up with the details in our maintenance departments, but at some point you have to concede the fact that a technician or two technicians working together are probably not going to be able to remember 39,422 tasks in a small production cell. The devil is in the details on our machine lubrication work plans. So to get those details in the right shape, we're going to go about devising a plan that puts our weekly work activities into routes where each task is addressed. We're going to record machine name and number, log the types, any other meaningful design details and environmental influences. We're going to, well, I will say you should build a map that shows where all of your assets are with respect to tanks and walls and motor control centers and what have you. This can be done easily enough in Excel. This is an Excel generated graphic. Once you have a map that shows the view of all machines, then you can efficiently devise a pathway that gets you from one end of the production department to the other with the shortest number of steps as needed to address all machine working parts. This is the route. Once the route is defined, then we're going to go back to the machine, record details about the individual components, and there's a lot of details to be recorded. The motor, who made it, the model, possibly, the number of motors, the number of components, the fact that it's a bearing, but the type of bearing, SKF, ball bearing, deep groove ball bearing, it's noted over here, and similar level of details for every lubricated machine part. None of these detail collection bits are complex, but it is time consuming. And if we want to have a machine lubrication program that supports that red blood cell thick layer protection, and we want it to be right, then we have to have the details in order to build that plan. The environmental characteristics are also particularly important. The more aggressive the production environment, the more frequently we should be working our inspections and applications. The information we're going to use to build this plan is going to come from a variety of sources, including standardized procedures, ASTM, ISO, DIN standard procedures, and other generally recognized engineering application definitions. Let's take a quick look at what that looks like. And we'll start with bearings. And we'll start with electric motor bearings. Come on, slide. There. We'll start with electric motor bearings. We'll look at the nameplate. We'll identify the bearing descriptor number. This is an ISO or DIN standard number. We can identify that it's a ball bearing. We know that there is a limit to which grease will function well in a ball bearing. So we're going to figure out whether this particular ball bearing falls above or below this speed. It's a simple calculation. ID of the bearing plus OD of the bearing divided by 2 times the shaft speed gives us specific values. Once we know the value, we compare it for the inboard or load side and the non-load side bearing to our limit for grease effectiveness, and we get a straight up answer. Grease is going to be a good fit for this component. The next question is going to be, how thick does the oil from the grease need to be at operating temperature to give us the means to float that element? That's a simple calculation. We can either drop the details into a calculator, or we can go to our bearing manufacturer's lubrication guide and plot the same details onto a chart like this. We come up with a drop dead point. Whatever that number, whether it's plotted or calculated, multiplied by 3. In this instance, for this bearing set, we're looking at a drop dead of 15.2 centistoke viscosity at operating temperature. Multiplied by 3 gives us a target, so that we're going to go try to find a grease that gets us to 47 centistokes at operating temperature. The operating temperature is 50 degrees C. We look at a product that's got an ISO viscosity grade of 100 that we're using on motors at 50 C. That viscosity grade of 100 gives us 60 centistoke of working viscosity. We said we wanted to have 47. That would be ideal. As it turns out, the product we're using would be ideal, and we move on to the next step. When calculating the viscosity requirement, we want to get to a space between 3 and 5 times that drop dead value. That is obviously greatly influenced by the operating temperature of the bearing. So we also need to know the operating temperature of our bearings and other lubricated machine parts when we're designing a program. Step 6 is about lubricant selection. Bearing manufacturers along the way have said it would be better if you're not using EP formulated products. EP attributes by design are somewhat corrosive, can particularly attack soft metal surfaces. If we don't need EP formulated greases, and we shouldn't use them. The drop dead viscosity value is the break point that tells us whether or not we should use EP products or not. In this instance, we picked a product that puts us out here just above 3 times the drop dead point. So we don't need EP formulated products to be able to expect to protect the bearing surfaces. The 6th point would be one of volume. It's a simple calculation. We want to fill the space that exists between the axial planes and the vacant space around the element. We calculate that 0.005 times the outer diameter of the bearing times the width of the bearing gives us a value in grams. That's a simple formula. Works on all types of bearings. This is the correct volume defined. And then we can verify that with different tools. We can put in the precise amount if we have the right equipment. Using ultrasonic energy testing, we can even demonstrate that we need more or less dynamically. The last point is about the frequency. Now, if we need more grease in a bearing, we should adjust the frequency to get there. Within a few seconds of supplying the grease to the component, all of the fresh grease will have flushed out the raced faces, and now it's sitting on the sideline. If we need more grease over the course of the working duration, then we need to take our big interval and chop it up into smaller pieces. All of our bearings would really rather be lubricated with oil, but we can approach that kind of attribute using grease if we are planning and scheduling the right frequencies. Here's a formula that can be used to determine a frequency. It is modified by the K value, which is the environmental conditions around the operation, the speed, the bearing temperature, the contaminant load, the moisture load, presence of shock loading, whether it's a horizontal or vertical axis shaft, and then the bearing type itself, all factor in to determining how frequently we ought to be lubricating the machine parts. None of these details are complex, but they all need to be captured and factored in if we want to have a precise lubrication work plan. Along the way, including from the previous discussion, we heard consideration about condition monitoring as a means, lubricant condition monitoring versus vibration-based bearing condition monitoring. Well, an option for our grease lubricated components is ultrasound measurement. Ultrasound measures contact energy. It's a much higher frequency than vibration energy, which measures the movement, not the contact. Ultrasound tells us when the asperities are beginning to bump and collide, and if we have high decibel values, that means our bearing surfaces are approaching a dry state. When we lubricate, we refloat the surfaces, the decibel value declines, consistent with less contact energy, and we're able to use this to dramatically, I shouldn't say dramatically, to effectively control volume being supplied for each component. There's rules for bearings. There's rules for couplings. Different kinds of couplings, different centrifugal force values related to the operation of the coupling. Different greases would be applied based upon the degree of centrifugal force loading on the grease. It's all fairly well objectively definable. Grease characteristics for those 3 different types of greases. We need to pick the right type of grease to match up with the coupling's operating conditions. There's rules for gear drives. And whether it's bearings, couplings, or gear drives, all rules ultimately boil down to speed and size of the machine part. The pitch line velocity is the required working viscosity for a given gear wheel in a gearbox. We know the pitch line velocity, which is a calculated value, pitch diameter in millimeters times the speed of that wheel divided by. And if we know the temperature of the oil in the machine, then we can clearly identify the best fit lubricant that fits that speed at that temperature. Very objectively definable. Fortunately, our gearbox manufacturers have done a good job of defining this and putting information on nameplates that go on our gear drives. They've done that for us. The pitch line velocity is the speed that this dotted line is moving in circles. The pitch diameter between the two gears is the point where load is transferred and rolling contact occurs. So that's the critical value. The gearbox manufacturers many years ago began putting the correct product definition according to an operating temperature range on their machines. All we got to do is go look at the machine, get the correct temperature and or the ambient temperature, and match up what the provider is providing, the lubricant supplier is providing, or the technical spec for the machine itself. Gearbox manufacturers use nomenclature for lubricant definition that's similar to what the rest of industry uses, slightly different, but the match is easily made. So regardless of the component, we got some calculations that we need to do to come up with the objectively defined best possible plan for all of our machine parts. Now we might well conclude, yeah, we don't have enough money in our budget to do that for all machines. Well, that's fine. Focus on the top 20% critical assets. Those are your bread and butter and safety concerned assets. Focus on those. Build the plan. Live it for a year, 2 years, 3 years. Begin to enjoy the benefit of that plan and see how it works out, and then transfer that well-defined, precise lubrication plan to other assets. There are tools that assist with the aggregation of the details. This tool called Lube Coach Pro is useful for getting all of the machine details together in one spot that gives you, the user, the means to produce an output that represents a vigorously defined lubrication plan. From there, it is tempting to try to put all of this information into conventional CMMS programs. We have many: JD Edwards, Maximo, SAP, well-known, excellent programs, excellent software, but those programs do not provide spaces for these details. So as it turns out with conventional CMMS, you're writing up individual work plans based upon text scripts. Go find yourself a task management system that gives you the means to organize your tasks in that linear sequence that you've defined. And then when you schedule that particular production department, you have the tasks that are due for the week that are all assignable and trackable to. And if you pick a system that gives you this feature, you might even be able to recycle tasks that were simply identified as incomplete without any extra effort. Here's an example of a written output. Mostly people today are using tablets to keep up with and record the completion of these details, and that's the smart approach. Your task management software should also, because all the details are based upon data fields, should also give you the means to generate rich reports on important things like what percentage of the task did we get done this week? How were we doing for this month in completing tasks on the first schedule? Now we should be at 90% task. And if we can't get there for a given route, then we need to move tasks around to other people, redistribute the workload so we can consistently hit 90% of task completion. You might want to track lubricant consumption. How do we control cost if we don't know where the cost is incurred? Anything that is within your system can be turned into a query and output. And with the benefit of our business intelligence systems today, that information can roll right out the front gate electronically up to the corporate office. And now we're not fielding phone calls every time we turn around either. Without a quality plan to manage the many, many details and a real, true getting those details accomplished each week, we are likely to drown in the complexity of our machine set of lubricated machine parts. We need a plan. A good plan will provide us the means to govern our work practices and control mechanical reliability of all lubricated machine parts. There's always room for improvement as well. Targets, 90% completion. Review oil analysis results bi-weekly. Implement vigorous contamination control limits. We didn't get into that, but a huge influence on your success, particularly for oil lubricated machine parts, is contamination control. Your technicians need to contribute from the chin up, not just the chin down. They need to have an education in the basics of machine lubrication, understand what the relationships are, understand the why behind the what you're asking them to do. And then you should look at your program on a quarterly basis to compare against your existing reliability goals and see if you're still moving in the right direction.
So I'm just gonna have to jump in a little bit because we're just at the almost at the closing time, and I know we had just one question.
Yep, go.
So we had one person, Mohammed, asking if there was a relationship between the motor grease drain point and the exploration area. So I'm just gonna bring that up on the screen here for you to help us a bit. So is there a relationship between motor grease drain point and the exploration area? Because we were talking about the exploration area in terms of, determining where we could get that perfect grease point and that, trying to figure that part out. So can you help us with that?
All right. There's a misnomer about drain. The grease that goes into the motor is going to stay in the motor 9 times out of 10, regardless of how much grease you attempt to push into the motor for flushing purposes. You're not going to get any grease out. So that excess grease is going into the stator cavity and will corrupt your motor. I'm not sure what exploration area. I'm not sure what we're leaning on there. Sonia, if you could provide him with my email address, we can beat on this more thoroughly.
Definitely, because that was one of the main questions that we had there. And I know that, like, just from the information that you shared, very detailed, very interesting things. We always need to be able to, calculate the right grease that we're using, because half of the times we're not using the right grease or the right viscosity. Yeah, suited for our temperature, suited for our operations. So I'm so glad that you were able to share that with us today, Mike.
Yes,
and
ma'am.
I appreciate so much
Thank you for
taking the
the chance
time
to visit with you.
to stay with us and share that information. I know some people were asking about the slides and if they can get access to the slides. I'm gonna leave that up to you, Mike. If you all want, reach out to Mike Johnson. He is on LinkedIn. And of course, we can provide his email address to you once you all just send us a quick note.
Sonia, if you like, I can send a PDF copy to you for distribution, but I would love to hear from your attendees as well.
Oh yeah, because we always like to hear feedback with LRVS. It's a community after all. Yes. So that's what it's about. But thank you so much, Mike, for your time. That was one of the main questions that we had. I know we'll have some others coming in. And I love the fact that you set the stage for Blair and talked about ultrasound. Well done. Because he is up next in the next 5 to 7 minutes. So we will be seeing him soon. So all of our attendees, you have a little 7-minute break in between. And we will be back in a little bit. Yeah? All right. Thanks, Mike.
Thank you.
Bye. All right. We are going to be getting ready to welcome Blair Fraser in a little bit, coming to us and going to be telling us so much information. We have Blair with us about manual greasing and moving that to autonomous lubrication. Now, it's all about the evolution of bearing technology, and who better to tell us about that than Blair Fraser? Yeah. So, Blair, I'm going to give it over to you. And, thank you so much for sharing your information with us, sharing your time with us. We know you're a busy guy. A busy
Always a pleasure, Sonia. Always a pleasure.
guy. So, I know I'm going to pass it over to you to take us through everything that we need to know about manual greasing and autonomous lubrication. So, the floor is yours.
Thanks, Sonia. And it's definitely not everything we need to know.
Just some of it.
Yeah, from an ultrasound perspective, definitely, Mike, and I always admire his talks and his knowledge when it comes to those level of conversations. So yeah, absolutely. As I get into this, what we're going to talk about is, and I think a lot of this can get applied to just technology, innovation, and evolution over time, right? And if you look at it, and there's been numerous papers written about the adoption of technology and how technology gets adopted, and really what the fundamental belief is that the human has a linear brain. We think in linear steps. And particularly, I see a lot of us, and I see some familiar names, are technical engineering background. So we are literally trained to think in linearities, and really technology and technology innovation is exponential. And as we get into this spot around even condition-based lubrication, I say condition or ultrasound-guided lubrication, we before we get true mass adoption, we get into this spot where it looks like the technology isn't getting adopted, and it's right before it starts to get that exponential curve. And that's what we're talking about here today, because for the first time now we have these systems out there that can autonomously lubricate our bearing, but not by time based, but by condition. So as we look through this journey here, and this is interesting. I think this speaks to the era we're in, because I did not create this image. I am by no means an artist. I used generative AI to create this image, and I had a conversation with it saying I wanted to create an evolution of lubrication, and it came back with this weird picture I couldn't explain. But then I started giving it more information, and I said I want to show the same person. So if you look at this person's face, they should be similar. One's got a pretty wicked beard, being in the caveman era, but is that evolution of bearing lubrication really? This is a great example of technology, like, data back to whenever we figured out seed oils and things like that. We're really good at helping us lubricate wheels, to now is a lot has changed. And Mike was talking about that, right? The right selection and things like that. But the apparatus of which we're applying it really hasn't changed. We're still using grease guns and things like that. Understanding cavemen didn't have that. But really, that's a great example of this evolution over time. And this is a great example of where that exponential curve is going to come in from a lubrication point of view. So regardless of the study, and if anyone that's heard me talk before, is it doesn't matter what study, and the reason why LRVS exists, and why Mike Johnson has a services to help people get lubrication right, is it doesn't matter if it's 60%, 80%, let's call it 70% in the middle, is we all understand now, and it's been proven time and time again, that lubrication, and particularly what I'm talking about is rolling element bearings, is the primary cause of premature bearing failure. And I truly believe it doesn't matter what the percentage is. It's really that it is the number one contributor to bearings failing prematurely. And RCM came out late 60s, really progressed in the 70s, and then now it's mainstream. It's a common term we learn. We're starting to see universities actually teach the concepts of RCM, and really what it taught us is, can we move back on that P/F curve? We treat things like systems, but can we prevent failures from happening in the first place? And that's really what we're trying to do here with autonomous condition-based lubrication. And when you look at these studies, now this is just one study for reference. I'm sure Mike and the team would agree with these findings, not necessarily the exact percentages, but really what we're looking at is, it's not just the right grease. It's contaminant free. It's getting there at the right time. And traditionally, as we look through this evolution, we have built technology to address one or two of the failure modes or failure mechanisms within the premature bearing failure, but we never created technology that addressed all four. And is likely why, still to this date, we have challenges. We have plants, facilities that are still experiencing premature bearing failure, even though they have put the latest technology in. It's because it wasn't addressing everything. And really, when we look at the evolution of bearing technology, of the evolution from going around with a manual grease gun to where we are today with autonomous remote condition-based lubrication, is addressing all four of these failure modes in one solution. So as we look towards this, and again, this is the evolution in Blair's eyes. It's not chronologically correct. There is some challenges to go through here, but I think you're going to start to see the evolution is what has happened over time. And I'm going to describe it as I know it. Now, I've been in this industry a little bit longer than I want to admit. Now I can't believe how much time has gone past. And I actually started my career on the plant floor, lubricating equipment. And I often say I need to go back to those employers and apologize. I'm not going to give them money back, but I guarantee now that I know I inadvertently caused premature bearing failure. Likely I wasn't an employer to experience those failures and I moved on to a different job, but I really need to go back and say something to them. So really the first evolution is, and it goes back to, seed oils and things like that, is whenever lubrication. And, and I still get this when I talk to customers, when I talk to clients out there is, what is your lubrication strategy? Well, I lubricate when I get to it. Right. And what's the old saying? If a little bit is good, a lot is better. So we still have a lot of facilities using whenever lubrication. And I would put whenever lubrication and OEM lubrication kind of in that same bucket. I think OEMs are getting better with the help of people I see on this call to understand that context matters, that if you put a piece of equipment, I'm in Canada in the winter, although it's abnormally warm here, or we give it to Sonia in Trinidad, there's going to be different lubrication needs that have to happen. So we still have whenever, whatever lubrication. But we started looking towards getting more scientific, which I think is great, which all these steps helped in the evolution of this technology and in the adoption of this technology. So we get to root-based lubrication. And really what we got good at is very smart people created some formulas to help us determine when and how much, that re-greasing frequency. So we got a calculator, we got a calendar, and we got a grease gun, and we got a human. We got a human going out there and squeezing grease. Some good, some bad, right? Along with that. And I'm going to go into some of the challenges we face and how we eliminate that with technology from route-based. And then we moved up to condition-based lubrication. UE Systems celebrated our 50 years. We've been in condition-based or what is known as ultrasound-based lubrication, where we're looking at the condition measured by the friction. So ultrasound measures the friction in the bearing. Now, and the reason I put friction in brackets on that slide is I have met people and I said, what kind of strategy are you using for lubrication? And they said, we're using condition-based. I said, that's great. Are you using ultrasound? Maybe using vibration, particularly in peak view or delta jerk and things like that. That's progressing. And they said, no. I said, well, what kind of condition? They said, well, I use the field condition. I said, oh, gosh, this is a great technology. I need to explore. So what is this field? Where do I get some research on this? And they said, well, what I do, Blair, is I get my grease gun, which undoubtedly is, thousands of PSI. And I put it on the grease port. And then when I was applying grease, when I hear just the slightest, or I feel just the slightest pushback of back pressure, that's when I stop and I know it's perfect. Right. So there is different concepts around condition-based lubrication. And obviously we know the power of these grease guns, specifically as, I understand this and I don't want to take this the wrong way, but as we get maybe a little more complacent, there's powered grease guns now, which definitely has an applications on some assets when you're purging and stuff like that. But if you have a 50 horsepower motor and you have to put a battery into your grease gun, I would question that. So there is different types of condition-based lubrication. So as I use it throughout this conversation, keep in mind I'm thinking about or using condition-based synonymous with ultrasound-based lubrication. And then 3 and 4 really came out at the same time. It is a race to figure out which one came out first. And to be honest, it's not worth our effort to figure out which actually one was patented first and things like that, because it doesn't matter. But we do have these automatic lubrications. They can be single point lubricators. They can be lubrication distribution systems with progressive blocks in them. But they are out there, and they're out there plentiful, right? And they actually combined number 2 and number 4 together. So instead of having to go out there with the grease gun, we have these single point lubricators that are out there applying grease on a set schedule. Now, if you got the schedule right in the first place, that doesn't change because of operating variables, then you can be in the ballpark. But anybody that's listening to this, I'm sure you have been on or you've used these, and it may be a love-hate relationship. Well, they're out there, but I still have to do a PM, a preventative maintenance task based on the calendar to check to make sure the lubricator is actually working and it has grease, the battery's there, hasn't fallen off, those type of things. So it is a love-hate. And as I said, 3 and 4 really came out together. As we shift to autonomous condition-based lubrication, it's really combining 3 and 4 together to make a solution that addresses those 4 failure modes of that premature bearing failure. So we're really combining technology that existed into one solution. So some of you have seen this, and I think this is a great example of where we have evolved, where we've put a lot of science research into getting us better results with our bearing regreasing. And this is an example of a calculation, which I think is fantastic and likely better. It's definitely better than whenever lubrication, 100% hands down. If that's going to be your journey, then head down towards that, put some kind of reasoning behind it. The reason I'm bringing this up is as you look at this calculator, and now there are many calculators that are out there, is in particularly, if you look at the right-hand side, the correction factors is as we become more variable with our operations, with our facilities. Tell me a facility that doesn't have to change something on a regular basis. And that can be just because of where you're located. An example I'm going to give, if you have a rooftop exhaust fan, here where I am and just outside of Toronto, our winters are very different than our summers. And look at that temperature. Housing, just the housing. I'm assuming just picture a pillow block bearing on the roof of a building in our Canadian winters. Yeah, it's pretty cold. In our summers, believe it or not, it gets pretty darn hot, right? So that factor would have to change. How often are we recalculating these type of intervals based on those type of parameters? And if you start to look at here, moisture is a thing that varies, maybe not because of our process, but because of the environment, right? And I think this is where, OEM frequencies and things like that can really get challenged because they don't know where we put their equipment and how we treat their equipment. So while this gives us a good reflection point on where we're at with our lubrication, sometimes it can lead us down a path that is not ideal. It ends up calculating regrease quantities and regrease frequencies based on what we think, not what is actual. And one of the big ones we're seeing, and this comes from 11 years in the automation space, looking at control valves and things like that, is a lot of plants are becoming variable in terms of their processes, and they're moving away from control valves, putting VFDs. We're seeing more and more VFDs or VSDs being put in to control the speed of these motors. So what happens when you're N? That if you look at the N here, that is a pretty important calculation on the denominator side. So if you have an asset, and we've seen assets go from 10% speed and 90% speed in one day, how does that affect this calculation? So this is just an example that I put together prior to this, just to give you an example, using that calculator. The only thing I changed, and I picked a pretty common bearing, the only thing I changed was the humidity. And right now, I believe it's 80 degrees plus in Texas right now. So they may actually be getting some humidity in February. So what if that moisture was to change from, less than 80 to 80 to 90? We would go to 79 to 81. What would that do? So what's interesting, if you look at this calculator, is the volume at 40, let's call it 41 grams. And there's another concern. Would you actually be able to put 0.85 grams into a bearing? I'm going to guess you're going to get to 40 or 41. But that interval went from 6 months to 4 months because of one slight change, right? And obviously there's no operating context. This is a hypothetical situation, but you can see the variability that's going to happen. So while we got good at a calculator, we got good at walking around with the grease gun, they're still subject to change around the variability in the way we operate, maintain, and where we place our assets. So definitely a challenge from that point. So we tried to solve this. Okay, we don't have, and particularly, and as we were trying to develop this next evolution of technology, we met with hundreds of customers and asked, hey, what do you like about single point lubricators or distribution systems? What do you don't like? And really, I got two answers. One is I've used them. You can go grab them. They're out in the garbage bin. Or two, we use them because it's the lesser of two evils. One of those situations where it's just unsafe to put a human to go in to lubricate, or it's enclosed from guarding, those type of things where, it's really the only thing we do. We'll never put a human in jeopardy, or, we're resource limited. And even if these fail, it's better than us not doing it at all. And I agree with that. And this is just an image off the internet when I looked at this around saying, hey, common single point lubricator failure modes. And this image came up. And I think this is great because what we've seen is this lubrication device is meant to, it is autonomous. It's meant to lubricate based on the time you put into it. But we often find people went in and put preventative maintenance tasks, so time-based tasks to go check to make sure things are okay. And I can't tell you how many times, and I have some videos, unfortunately I can't share them, but of lubricators on the ground. I have one that was completely full of water. It looks like it went into a pool and they put it back in there. So obviously the LCD wasn't lit up and things like that. So that's some of the challenge you have with these devices. And I say this respectfully, but somewhat dumb devices that are out there. Understanding there is some now that can give us feedback. We can get some insights into a PLC and things like that, which I think is great. That's the evolution of technology that we need to get to. Some incorporated some sensors, not to do condition-based lubrication, but to answer some of those variables we had in that time-based calculation. Duty being one of them. How often and how many of you are listening to this that have assets that may have redundant? I run this one for a week, I run this one for a week. Or I have a batch process. Every time I run a batch, it starts up, then it sits down, right? So the duty is really important. So if you have a sensor in there that can figure out if it's running or not and lubricate while it's running, is going to make it more intelligent, but it's not going to solve all four of those issues. So we move to condition-based lubrication, and it becomes very simple. The technology behind the scenes of how we measure the friction, how we measure ultrasound, how we get that decibel level reading is sophisticated, but really from how we use the measurement becomes very, very simple. From this aspect, what we do is we measure the bearing friction. The ultrasound is proportional to the friction in the bearing. Corresponding increase in that decibel, that friction level, indicates the first sign is it needs lubrication. The second sign is it's beyond a lubrication failure mode, and the third sign is it's walking beside you down the hallway. So I'm going to, and understanding this is a lubrication focused group that we're talking about here, so I'm not going to try to butcher the Strybeck curve, but it is important to look at this as we look at the Strybeck curve, and really where we're looking at, and understanding this is a rolling element bearing versus a Germer bearing, so we're going to be a little more aggressive towards the mixed domain versus the hydrodynamic domain. But really, if you look at that friction over a course of a rolling element bearing, is in the first regime we have the boundary, we have metal to metal contact, right? That's the highest level of friction we can get into a bearing. In fact, when a bearing fails completely and the rolling elements fall out, there's actually no friction. And then now the shaft might be banging. So it's kind of interesting that way. As we start to add grease, we start to reduce that friction. As we start to over grease it, because we're getting that hydrodynamic, we're overfilling, those rolling elements have to push against the existing grease that's in there, creating friction. We start to go up. So with this technology, we can start to look at not just under grease, but over grease as well. And essentially what we're able to do with this technology and autonomous condition-based lubrication is really play a game of where we are at. We've gamified that Strybeck curve. I'm going to play a video, and this gives you an idea of condition-based lubrication, but doing it manually. And even with this technology, there are things that can be are not ideal from the best practice. So what I'm going to do is, this is our Ultra Probe 15,000. It's actually our later model. The gentleman behind there is applying grease. Don't know this asset, don't know the context of it. But as you look towards this, you can see the starting friction of this bearing is around 57 decibels. So grease is getting applied. one thing, and I think it was Mike that might have mentioned it, is overgreasing is not just too much grease. The rate at which you apply grease is also very, very important. Every time I watch this, I get a little bit nervous about that. I don't know the context of this, but there's a lot of grease going in in a small amount of time. So if you look at that decibel level, it dropped down to 42, 43. That's what we call the aha moment. We went down that Strybeck curve as we added grease. I feel like I should yell, stop to this person every time I see this video. I'm just going to make myself feel better saying they did this for educational purposes, but I don't know if that was true. So as you see, he still applied some grease, and that we started going back to the right side of that Strybeck curve. So even with condition-based lubrication, there's still a human in the loop part of it. As we look at what does an autonomous lubrication system look like, well, we need a lubricator. We need a lubricator to put grease into the bearing, right? That takes the human out of loop. No longer do we have to go out there and squeeze a grease gun. Not saying this applies to every bearing in your facility, but that's really what we're looking at is, we need a lubricator that can, when called for, has the smarts. So it can tell us its grease level, can tell us if there's back pressure building up in the bearing itself. If you mount this 20 feet away and use grease line to bring it in, is there any blockages? Those are the things we need to give us that trust back into these systems. And then we need a sensor. We need a sensor to measure that friction level, and also look at it from another point of view is other failure modes that may happen other than lubrication. And we need a place to bring that data to and look to it. And we need a way to get that data digested from site into the cloud. That's the technology evolution we're talking about, replacing a person and a calendar and a calculator with this. So as we look what's happening here, as that bearing is rotating, it starts to need grease. We're exaggerating this with, with the bearing looking like it's red hot, but there is ISO limits. It's not like we're picking a spot on a dartboard saying, I think it needs grease around this point. There are some changes that we need if based on operating context, if it's on, off, or very, very slow speed, less than 100 RPM, we will customize those alerts. But really what it's going to do is apply grease automatically on our behalf, very, very slowly. So if you saw the video previously, the gentleman was adding grease. In my opinion, now I don't know the context of this bearing, a little bit aggressively, but understanding if you have to lubricate 50 bearings in that shift, right, you're going to want to move it through pretty quickly. And with an autonomous condition-based lubrication system, you need to look at the methodology of how it's applying grease, how it's measuring that friction while grease is getting applied. So we know if it needs to continue greasing and things like that. So this is an example of that friction level going up, lubrication being added, and that friction going down. And I'm not going to get into what that yellow line behind it, but it does matter as well, because it gives us a lot of confidence that grease is hitting the bearing and things like that. So that's really what we're looking for. Can you imagine where you have your important essential and critical assets being monitored by a grease expert 24/7. It's looking for that. It's looking, say, hey, you need grease. It could be the middle of the night, but I just greased 2 days ago. Well, you actually have a defect, so you need more grease more frequently. The system is going to do that for you and apply grease. So what does success look like? And this is our older platform, but we've had autonomous condition-based lubrication out for well, we're getting 3 years now. And, one of the things about technology and the evolution is being able to learn. We've seen good bearings being lubricated. We've seen bad bearings being lubricated. We've seen bearings with defects being lubricated. And specifically after the pandemic, I'm not sure what drove this. The number of counterfeit bearings, particularly outside of North America, is staggering. How do we know? Because the friction level is off the charts right from installation. And unfortunately, we have seen a number of counterfeit bearings get to market and get installed into equipment. So what you're going to see here is this is the friction value. That green line here is the baseline. This is ideal friction. It's not necessarily the bottom of the Strybeck curve. We do go a little bit to the right, just facing the hydrodynamic, but not quite that far over. And what you're seeing here is that friction level rise. So why is it so choppy? Because the bearings are choppy. It doesn't, even the healthiest bearing, you're going to have peaks and valleys within your friction, but very minimal point of view. So this is a great example of that friction level going up. This blue line is when it needs lubrication. How simple is that? System kicks in, starts to lubricate. What we start to see is that friction level drop. Just like we saw that gentleman apply and that ultra probe start to show that friction level drop, this does it automatically. What we can see here is, now when I took the screenshot, it was 4 days ago, and he used 9 cc's of grease. The baseline right here is 11 decibels. That's where we want to keep this as much as we can, right? The starting friction was 22. And if you know ultrasound, you'll know 6 decibels is around doubling the friction. It's not a linear relationship. It's exponential from that perspective. So we dropped it from 22 down to 12.6 decibels, all automatically. So it slowly applied grease as that was dropping, hit the bottom and kept there. So one thing you can see here is, yes, it lubricated, but also keeping that knowledge. And I think that's where without data, if you don't measure, you can't improve. You can't improve what you don't measure. Can we get some of that information? Can I look at this bearing? How much grease am I using? Can I predict how much grease I'm going to use? So absolutely. So use 9 cc, so around 9 grams of grease, which is very minimal. As we look for it, and what we've seen is we have learned so much over 50,000 data points, thousands of sensors out there streaming friction, lubricating autonomously out there. And, we've seen things, and this was an example done in a lab where we started to see this micro explosions happening within a bearing. And we applied with a grease gun, in this case, just a little bit of grease just to see what would happen. And we noticed right away that it went nice and quiet. So as we're still building on this technology, we're taking from that 50 billion data points and learning to see, can we further optimize? Can we predict when lubrication is required, and we can fully optimize the lubrication schedule? Now, some of you may have slow moving bearings, and this has always been a challenge, particularly with even condition monitoring, because slow moving bearings, vibration is a pitfall from slow moving. And I traditionally understand slow moving, has to do with the pitch and things like that, not just the speed, but generally we like to think about around 100 RPMs or less. You need to look at a new approach into the lubrication. So this was a great case study of 1.8 RPM. Do not go to a bagel factory when you're hungry. It smells so delicious. And so bagels are coming through and they're getting baked. 1.8 RPM bearing. It's one of the ones you have to put a chalk line on to make sure, is this thing still moving? And you can see even at that slow speed with the sensitivity of the sensor, you can see a drop when grease was added, 0.3 cc's, right? That's typically what you wipe off the end of a grease gun. That's a small amount of grease made that much impact to the friction trend. So what I'll do is I want to save some time for questions. You're welcome to reach out to me directly. Here's our email twice. Our website is uesystems.com. If you have any questions, I'm happy to answer any here, Sonia, or you can pass along my information.
Oh yeah, definitely. And I agree, it's never a good idea to go into a food factory when you're hungry, especially when you're doing any sort of condition monitoring, or you can change your job to quality assurance there and just say, you know what, I'm here for quality assurance.
That's right.
Let me just test it. So we had one question coming from Peter, and Peter's asking about those micro explosions and if those were asperity contact events.
So the answer is yes, and there's actually a research paper done behind it. I don't own the paper; we supplied the technology, and obviously it's leading into something great. I'm going to talk to the author of that, and Peter, if he is willing to, I'll get you in touch and answer that questions, because it's over my head from that aspect of it. But the short answer is yes.
Okay, good. I like that answer, because a lot of times we see the guys with the grease gun and they're going around and they're like, yes, let's do more grease, but I'm so glad that you highlighted the repercussions of that, and that's something that we can all learn from the what's going on right now. I know Dr. Gary is asking a question. Have you correlated your friction observations to torque and power consumption?
Gary, if this wasn't virtual, I'd hug you or at least shake your hand from that perspective. So what I can say with a high level of confidence is yes, it is something we're doing through research. And yes, there is very small, obviously, because what we're measuring from a lubrication point of view is a very, very small change in friction. And of course, if you look at a motor, power factor, kilowatt, very variable. But the answer is, have we correlated it? No. Are we correlating it? Yes.
It's all in the works, Gary. All in the works. All in the works. Because I know, in terms of, we're always going back to that baseline. Okay, what is it that was the problem that we're trying to solve? Friction at the end of the day. So we go back to that. I love the fact that you're bringing the stride back curve. I love the stride back curve.
That's right.
But I love that you're able to bring that to the audience and to help them to understand that. And I know Mike Johnson is, chiming in there that this innovation will deliver the promise, the very good promise of true condition-based monitoring, true condition-based lubrication. Because nobody likes that. Nobody likes that 12 a.m. call, 12 midnight call. Nobody likes that. Say your bearings are down or something is going on. So I love that we get to explore that. And I know Ahmed is also asking that all of these monitoring seems to be about greases. And what about the lubricants? Well, that is more on the oil analysis side. So let's give this one for the grease section, because I know they're handling that part right now. But the lubricants, that's another LRVS, Ahmed.
That's great.
Definitely. So I know we are just 1 minute over time. Oh, we have one more question coming in. From Praveen, he is asking if you have any data that can correlate remaining useful life extending for bearings with condition-based lubrication.
Yeah, and quite a bit, and that's something we're compiling over time. Absolutely. Now, where I thought you were going was predicting the remaining useful life using AI, which is a separate conversation, which I can answer. But data to support that using condition-based lubrication will extend bearing life or get to the L10 life. Absolutely. We have a number of case studies of doing that. The proposition that we really see and the value is threefold. One is you will see a reduction. If you weren't lubricating at all, you probably, and you have to start using grease, you will use more grease. But for 99%, we're talking about a reduction of grease being consumed, and the frequency may increase, but the quantity is going to be less. Two is that remaining useful life of getting your bearings to prevent downtime to get its design life. The third and often most valuable is the resource time that people get back, because they don't have to go out there and manually lubricate. You don't have to get a work order. Well, you still may have to get work orders, but you don't have to get the right grease gun. The ability to cross-contaminate grease. Oops, I put that wrong grease in, is eliminated. So that resource time is something we didn't realize is probably the biggest driver.
Definitely. And one more question from Praveen before we close off. Is it a wireless system with lubrication data hosted on UE Insights Cloud?
Yeah, and that's a very product related question. But the answer is yes. We've redesigned UE Insights, and if anyone wants to see data, we have live data coming in that we can share a dashboard. You can't lubricate, obviously, from that perspective, but it is that lubrication data coming in, and of course designed to get that data out. And we don't want to be, and I don't think anyone in the space should own all the data, so we designed it to get data out into other systems as well.
All right. I think that really answered the question. But Blair, always a pleasure to have you here.
Always a pleasure, Sonia. Thank you.
On LRVS. And, stay tuned. We have another, in the next 5 minutes or so, we have our final panel of the day. And they'll be talking all about turnarounds. So, that's not one to be missed. So we will be seeing you soon, Blair. And thank you all so much for tuning in. You all get a 5-minute break. Yeah. See you soon. Bye. All right, we are getting back to our last panel of the day, and I'm going to start bringing on our panelists. We have Greg Livingstone from Fluidtech helping us out with
Hello.
this panel, Robert Torres from Amber Industrial Services, and of course, Jim Hannon from ExxonMobil. So we have these three amazing experts that are going to be telling us a lot more about, preparing your lube system for a turnaround. And we know turnaround season is coming up. So I know these guys are going to be giving us some more information, what we can do, what we cannot do, what we should do, and what we definitely should not be doing. And I'm going to pass it on to all of them because they are the experts here. I know Greg wanted to share a couple of slides this morning. So I'm going to pass it over to Greg, and Greg can kick us off on, how do we even begin preparing for a turnaround, especially with your loop systems? That's the heart of it, definitely.
Excellent. Good morning, everyone. Nice to see you all. And I think one of the points that I wanted to make is that when engineers are planning for turnaround, typically they're looking at 12 to 18 months out, and they're looking at kind of a long-term plan. And so there's a tremendous amount of planning and project management work involved in organizing a turnaround. It's a very, very stressful time during a plant's life, during turnaround time. There's a lot of engineers that are getting very little sleep. You also have a lot of other contractors on site. So it's a very busy time. So I think from a lubricant point of view, the more forecasting you can do to be able to better predict what services may be required, what action may be required, I think would be, I think is super beneficial in the planning process. A lot of times we see lubricants are kind of something that is maybe overlooked in some planning, and so it's a few months prior to the outage, and people are like, well, what options do we have? The oil's in bad shape. Do we have time for an oil change? And so it's a little last minute scrambling. And so I always think it's good if you consider your lubricant like an asset, like all of the other assets that you're trying to maintain during your turnaround, then you should have the same kind of forethought with what action should be taken during the turnaround. So maybe that's my introductory. But before we talk about this slide, maybe Robert and Jim can kind of go through and give their view on this here as well.
I'll just offer a quick build on that. It's really important to have regularly scheduled meetings with your lubricant supplier so that you've built a rapport and an understanding of your equipment and their what they can bring to the table. And like this slide, it is a very complicated slide with a lot of different paths to take on it. And it's not meant to study and follow these paths, but the key elements are over there on the left, those key seven elements. And we feel like if you've got a good handle on these key points, then you're going to be in a very good position to understand what is your best path for that particular turbine at that particular time in the oil and the turbine's career. So and then we can go through that in greater detail later, but that just kind of sets the stage for the meetings that you should be having with your oil supplier on a regularly scheduled basis, and then you map out, maybe the plant has got 6 turbines, and you'd say, okay, turbine 1 is at this stage, and you go through each one, but you develop a holistic plan.
Yeah, I would agree as well. I think creating a really good, deep understanding between, your plant, your staff, your crew from the get-go, I think sets them up for a really good position to succeed. I think a lot of times before we even get to the maintenance strategies and in-service oils, it'd be a really good recommendation to sit down with your staff and say, look, turnarounds are stressful, right? Prep them. List all the negatives. Say this is going to disturb our operation. We might need to order extra parts. not planned for. The additional maintenance costs, there are a variety of aspects that even might contribute to the risking of safety. So after you get all those negatives out of the way, sit down with your staff and say, look, this is a planned shutdown. This is something that has been forecast out so that we can improve the efficiency of this plant. You would rather have a planned shutdown than an unplanned shutdown, obviously. And I think also try to catch the potential failures ahead of time. So if you're prepping your staff and making them really aware of that, I think it puts them in a really good mindset to be acceptable to a lot of change, because it is different from their normal standard shift.
Oh yeah, I love that. Definitely love that, Robert, because I think everybody going into a turnaround, there's always a little bit of anxiety of what can go wrong. And we know a lot of things go wrong, but being able to plan in advance and preparing yourself for that, that helps quite a lot. And I like what Jim said as well in terms of we know it's not a simple operation. It is complex. It is a lot of moving parts involved. So it's easier to just take it bit by bit. So I'm going to pass it back to Greg and help us go through this very easy looking slide that you have there.
Well, this is far too complex for me, so I'm going to pass this on to Jim with the.
Oh yes, definitely. Pass it on to Jim. Yes.
The flow chart is very complex, so we'll have the expert answer that.
And then just to say that, so Greg and I, and then Rig, put this together, and we worked on this quite a bit over the last couple of years to figure out just kind of that as a customer is sitting down to figure out, okay, I've got a turnaround coming up. What do I need? What do I need to prepare to understand what my actions should be? And really the key elements that to sit down, you have to take a look at, oil analysis. And when I say oil analysis, it's got to be advanced oil analysis. It can't be simplistic like just viscosity and acid number and water. We want the full test late. So that includes, and we've got more slides on it later, but that includes, your ruler numbers, your MPC numbers, your ultracentrifuge numbers, your FTIR for oxidation, your RPVOT, and a whole list of probably a total of 12 different tests that we want to see. And it's often best to get a trend of it, not just a one-time data point. And that's why the continual building of data and relationship is important. With all that, then you've got a pretty good start on things. And then we would look at, if you have the capability of doing equipment inspection. And oftentimes you don't, because the equipment's up and running. But there are times when the unit is down, and especially in those, like a GE turbine, where you can pull a servo valve and do a servo valve inspection or a last chance filter inspection. And or you could be studying your bearing temperatures and watching for any climbs in bearing temperatures. That's all kind of indications and could be captured under equipment inspection. Then we look at the oil service life hours, because we have a pretty good idea on the oil life expectancy. And so oftentimes it does get lost in the details about, well, I've got 34,000 hours on that oil. Okay, that tells us a pretty good story. Or I'm at 90,000 hours on that oil. Well, that tells us a different story. So really understanding those service life hours, maybe if there's a lot of makeup, understanding the makeup rates. Then also certainly understanding the in-service oil that's being used. And sometimes it's actually two different oils because of whatever reason, you might have two different oils in a reservoir. So understanding that. Also understanding operational issues. Am I having bearing temperature issues? Am I having a hydrogen seal temperature issue? Am I having sticky servo valves? All those kind of things, and then photo documentation of that is also very helpful. Then also understanding your operating profile. Are you cyclical or base loaded? And also, what are you going to be doing in the future? More base loaded, because if it's more base loaded, maybe you have less of a problem with sticky servo valves. And then lastly is that outage schedule. Okay, we're going to be down now for a major overhaul and we're going to be out for 3 weeks. So we can do all this stuff. Or in the next 18 months, I've got a hot gas pass inspection where I've got 4-day window. So all those things build into eventually going through that turbine oil triage.
Good. I love that explanation. It's very important to plan in advance. And I think being able to know what you have and what you're working with, that helps a lot. Your planning engineers are very important there, and especially your finance team, because they need to help us out with the budget parts. Anything else you all want to add for that, Robert or Greg?
Robert,
Sure.
okay, I'll let you go.
Yeah, one quick thing that James touched on was the documentation piece. I think is vital. I think the two major purposes for a planned shutdown would be to either correct some of the problems identified on the previous shutdown, or to possibly look into the next shutdown and what are the identifiable markers that need to be documented for the next shutdown as well. So when James touched upon details, I think that's a perfect example of documentation. You'd be amazed how much data you can grab from your cell phone, and operators and engineers can then regroup together during the shutdown in progress meetings on status updates, and then attention to detail. Those are going to be really, you're saving facts, because really on a shutdown, you want to catch your low hanging fruit first and then get to your more difficult systems. So when doing so, it's really the documentation piece, and really pictures and all these reports are going to be vital.
Mm-hmm. Definitely.
So one of the things that I think is we always get a lot of questions from our clients on the oil's at the end of its life. If they're doing a good job in properly preparing for the outage, they know a year ahead of time that in fact they're going to be changing the oil. They can make all the arrangements to bring in a tanker to bring to facilitate the oil change. But then there's a big question: should we flush a system in between? Should we? Unfortunately, I think a lot of plants actually don't go through this. They drain the old oil, put brand new, beautifully formulated, pristine oil into a dirty, messy system, and shorten the life of it, and it causes all sorts of problems. But I think that's one area that in the loop planning stage that I think is often overlooked. So I think it would be interesting. I think, Jim, I know you have a slide on this, but it would be interesting to get Robert's view on, if your customers that are considering, should I flush or not, and kind of what some of the different things they think about, in trying to prepare for that.
Yeah, I think one major factor when determination of flushing, or even James had mentioned a varnish, MPC and UC value tests, keep in mind that oil is going to be real happy when it's running at optimum temperature. So when it's running through your system and it is at temp and maintaining temp the entire time, people really fail to understand that when that temp comes down and on that shutdown, adversely, that varnish is going to be a real mess. It's going to adversely change when you go to start back up. Those things have to be assessed and determined, not just at running temp, but not at a running temperature. And then also the data is going to really support all these movements and corrective changes for maintenance. So the MPC and the UC values, they're great data, but it'd be nice to pull those at different timetables throughout the shutdown, so that you can have a better understanding and put yourself in the best possible situation to succeed.
Definitely.
Excellent.
Passing it to Jim.
And I just thought maybe I'd
Yeah.
advance slides here, and maybe Jim can talk about this a little bit here.
Yeah, and very simplistically, like you said, sometimes you actually if the oil's in good enough shape and you've got reason that maybe we've got our own refineries, right? And they said, look, we've got a turnaround coming. The oil's in pretty good shape, but we need it to last 8 years and we can't touch it. Okay, fair enough. And then it's kind of what the customer goals are, sets your plan forward. But maybe the oil is in good shape and you're just looking to have that extra boost of security. And maybe you'd look at all the data and all the elements of it and say, you know what, we're going to be okay with the drain and refill. But when we say drain, we certainly want to get below 5% residual. And kind of what you mentioned before, Greg, if that system is in bad shape and they just did a drain and a refill, you're going to leave 5% residual. And that 5% residual acts as a catalyst to hurt that next oil that comes in. And oftentimes we kind of see like a half-life. So let's say you got 10 years on the first charge of oil, you did a drain and refill, 5% residual. Well, maybe the next round you'd only get 5 years because you've got those free radicals that are now attacking that oil and making it a lot less, lot shorter service life. So that's the easiest, is just to drain and fill. Or maybe you say, you know what, this oil is in decent enough shape, but I still want to get it out. I'm going to go through a displacement flush. And we have different categories on why you would pick a displacement flush over a different flush. But basically, a displacement flush is draining the old oil out to less than 5%, putting in a charge of oil. It might be the same quality as the final fill, or it could be a flush oil. Those are kind of decisions you would make with your oil supplier. Circulating it on the system, pumped for 8 hours, draining that out, and then refilling, and then with your final fill. Or we've had great success now with the use of mobile solvencer to slash decon to put that in the system 1 month in advance, and then let it run for a month. And we put it in at a 5% concentration. Then we would drain that out to less than 5%. And then depending upon the quality of that oil, and it's a judgment call, whether we would need to do a displacement flush or whether we're satisfied with the work that solvencer has done, and we're now filling with the final fill. So in that perspective, we actually don't even have to go through that secondary flush. So that's an option. And or when needed, you can bring in the sledgehammer, which is, we have a product called Mobile System Cleaner that is a very good cleaner, but can negatively impact the following charge. And you certainly need to go through a very thorough displacement flush after using the system cleaner. And then lastly is a high velocity flush. And that is typically done on new turbine commissioning and or after a catastrophic bearing failure, and you've got to get debris out of the equipment. So there's a lot to talk about there, but those are the 5 types of flushes that you probably may be looking at doing it at any given time.
Yeah, and thanks for explaining that to us, Jim, because a lot of times people go into a turnaround and they think, okay, I need to do a flush, but I have no idea where to start. Like, I'm not sure what type of flush I need to do, what condition my system is in. And that's the thing with these turnarounds. Everybody's system is different. It's not a cookie cutter approach. We have to be able to assess the system that we're working with, the conditions that exist. And Robert talked about it earlier on, documentation. And documentation, that's where it starts really, because if you have no documentation, then how are you going to prepare yourself for this turnaround or the upcoming turnarounds ahead? And that's where it's so important to have this process in place. So I know we're talking about the different types of flushes, how do we assess and what do we do? But what would you suggest to, people who are now engineers who are now coming into the field and may think that TAR actually stands for sticky substance in the ground? What do we suggest to them? How do they start getting on board with understanding how do you prepare for a turnaround? What's the first thing you need to do? And I think the first thing you need to know that TR stands for turnaround. That's just me, ground base level. Yeah.
Well, I think one other thing is trying to pull together all of the relevant OEM recommendations, all of the other relevant specifications. So in terms of the world of flushing, the ASTM D6439, be sure that's right.
Yeah.
It's a flushing oil spec. Jim, you and I have contributed to that spec over the years, but it is really an up-to-date methodology on kind of going through some of the different approaches that you would use in flushing. So it's a fantastic resource, I think. So basically trying to gather as many kind of external resources as you can. I think that's an important kind of initial first stage.
Nice. Anything else you all want to add to that, Robert?
Yeah, I think there's a couple of categories. There's a sequence of events in which someone plans for a shutdown and plans for an asset to be either very invasively touched upon or just minimally invasive, where we're just doing a regular PM schedule. One would be defining the scope of work, right? That would be the number one starting point. I think developing a schedule for that definition of scope of work would be the next. You would then have to prepare a budget. I think the other portion that we don't overlook, but sometimes they're just not at the forefront, is making sure that this shutdown is fiscally responsible. Obviously, everyone has accounting personnel that they report to, and we have to operate within, a budget. So at the same time, we want to make sure that it fits the fiscal properties of the actual shutdown, and then communicate that plan to your staff, right? So if everyone has that awareness, then you're able to then execute the actual shutdown based on the plan. And the plan will change. It's going to be an ever-going change based on the findings that are contributing when you actually first pull that oil out, whether you assess your filters, whether you understand, wow, this, varnish has plated onto the metal surface. We actually need a more invasive absorption media to get rid of the varnish, things like that. And those are just a couple examples. And then the final step would be to evaluate the shutdown post. After all those corrective measures have been made, then you can reassess and get better for the next upcoming shutdown as well.
All right. Anything you want to add to that, Jim?
Well, and Robert brings up a great point about the documentation, because at the end of the day, and the turbine gets filled, you've got a good piece of paper that said, here's what we did, here's what we saw, and here's our expectations. So other than that, oftentimes, and I know Robert knows this, and so does Greg, that when you're talking to a customer about, well, what was done at the last change or the last overhaul, nobody knows. They just think it went from oil A to oil B, and they have no detail about how that happened. And then with Robert and good flush companies, they'll have a detailed checklist, and they'll also understand that changes happen, right? Oh, we couldn't get that valve open. We couldn't break that flange. We couldn't do this or whatever. And you just document it. It doesn't stop the process. You document that we couldn't get 8 hours of flushing in. We could only get 6 hours, or we went to 16 hours. That's all well and good. You just document it, and then you know.
Mm-hmm. And that's extremely important, Jim, because what we learn with turnarounds is that we're there to learn and we're there to put things in place for the future. So after the first turnaround, then you realize, okay, well, we were only able to plan for 6 hours, only able to get 6 hours of flushing in. So next time we can plan for 8 hours. Next time we can plan for 16 hours. So I love that. I love the conversation. And I'm just going to jump in very quickly with a question here that Greg already answered. But William is asking, how do you drain the oil after the solvancer flush? So I know Greg answered it in the chat a little bit, but I'm going to just bring it to the table because we have the experts here. So, Greg, I know you want, maybe you can start off with it and we'll jump into Jim afterwards.
Sure. Yeah. So if you do a solvencer flush, that basically that's inferring that you're trying to decontaminate the lube oil system in between oil changes. So in that case, you would, as Jim said, you probably use a 5% treat rate of mobile solvencer, and then after a month prior to the outage, you add mobile solvencer in, and then simply drain the oil and then recharge the system. There is another application where you can put mobile solvencer in long term for deposit control. To provide long-term deposit control as well. We would not call that a solvencer flush. So in that case, that could be a long-term application.
Okay, passing it to
And,
Jim. Just
yeah, I'll offer that on certain turbines, like in particular, like the GE Frame 7 FAs, that there are so many of these turbines in the market in US and Canada, and we've gotten a lot of skill at the conversions and that kind of thing. And one element we talk about is like the 19 low point drains on a GE Frame 7 FA. So you're going to all these low points, and then it's a conversation with the customer, like, do you feel comfortable with breaking this flange right here, putting a 5-gallon bucket? And that helps because it is beneficial to get the residual oil out as best you can without also being practical about it. But so those 19 low point drains, and we could talk to you about that in detail later, and or the use of shop vac in different areas where you're pulling a vacuum on and you're using squeegees. Maybe you've got confined space entry with people in the tanks doing hand wiping. A lot of that is dependent upon your schedule and also your concern about severity of the previous oil. So there's some decision making in advance. And then even as Robert pointed out, once you get into that reservoir, maybe you're making a game day decision because things are a lot worse than you thought, and we better do X. And so that's why you bring in companies that have a good track record and a long history of understanding what option A, B, and C might be.
I'm
going to just add one quick point to what Jim said here. Confined space tank cleaning and manually cleaning out the tanks, it's not it's probably not considered a really a job that a lot of people want to do, but there can be a tremendous amount of value in doing that. So if you are doing confined space tank cleaning, take pictures of the inside of the components, and if you find deposits, capture those deposits. And so many times we see, we'll see pictures of all of this varnish and deposits, and they'll have all sorts of really interesting pictures. But it would be so valuable if we could actually take that deposit and actually do some characterization and analysis on it and figure out actually what are the mechanisms that created that deposit. So I really view confined space tank cleaning as a super high value activity that instead, in addition to just decontaminating and cleaning the system up, you're playing detective, and you have an opportunity to really capture any strange things that you see. So take advantage of that during an outage.
Definitely. Anything you want to add to that, Robert?
Yeah, I would agree 100%. I think when anyone is planning an outage, the confined space tank cleaning is going to be your utmost, biggest physical representation of what is in your tank, because obviously the oil is doing what it's supposed to do with the ad packs. It's supposed to be carrying out all these contaminants out to the path of least resistance, and it's going to settle out in your bulk tank. Apart from that, maybe identifying a couple key locations as well besides the bulk tank, like maybe a servo valve, maybe your filter housings, maybe that GE turbine, like Jim stated, has 19 different drain points in which you really want to identify if there's more aggression on one particular drain point or another. But the confined space tank cleaning, like Greg said, is not for everyone. It is a dirty job. When we talk about dirty jobs, it's pretty up there. But it is a really good, gratifying sense that you got to the bottom of the reservoir, you identified any contaminants that are in the reservoir. What we normally do is we have a nice little collection pile and it's usually placed out on a white lint-free rag. And those physical representations can also really educate the rest of your staff and the individuals that were not involved in that particular shutdown. It is a really good learning tool that can be used between different refineries and different customer locations, whether they have a shutdown in San Ramon, and that physical correspondence of contaminants can be relayed and educated to a refinery that takes place down here in Southern California, or anywhere else, right? And so that documentation will help contribute to educating everyone and then maybe being more efficient on the next shutdown, because obviously for every minute that the refinery or plant is down, it is costly, right? And apprehension levels go through the roof at the later stages of the shutdown because everyone's apprehensive about getting the plant up and going. And as long as you're following those key stages and the order of operations, the attention to detail, I think is everything. But the good thing is we do have a lot of technology that will help us in the decision-making processes with these, additives and solvencers. I think they really do a good job of breaking down a lot of contaminants, holding it in suspension until you can actually schedule that shutdown.
Oh yeah, definitely. And I think that's one of the things that we learned. I want to say we learned the hard way initially. Just trying to get over those hurdles. And I hats off to the guys that go into those places. A lot of respect for you all. A lot of respect for you all. But if you could bring us back some souvenirs with those deposits, perfect. Absolutely perfect.
One other point I was just going to offer is like setting expectations. And so sometimes we talk to them about a solvent or a system cleaner, that kind of thing. And the customer kind of maybe expects that after they run that, they go into the reservoir and it's going to look pristine, like brand new day. And it is, because you've got years and years of varnish deposits, so mostly the bathtub ring in a reservoir, and that'll be like 6 to 8 inches of where deposits will settle, and that's fine. But the idea of scrubbing so hard to get that clean again is wasted effort, because they're setting on the reservoir walls, not harming anything, and so it can be. I've had customers that were upset, saying, "No, I expected this to be pristine." And it's just, if you let them know going in, it won't be. But the important part is your bearings and your servo valves and the key components are clean. That's where the money is.
Good, and thanks for bringing that up, because I know a lot of customers after after the flush and whatnot, that is a question that they may have. So I'm glad that you brought that up. But Peter is actually asking us, what is the reason for bypassing the bearings when you're doing a high velocity flush?
I think Robert has a flushing company, so why don't we?
We're putting Robert on the spot here.
Sure, that's a very important question, and it's a question that really needs to be interpreted when looking at a PNID or looking at the structure of that particular turbine or machinery or piece of equipment, because the reason why we bypass bearings, the reason why we don't really want to use the auxiliary motor or any of the items that are currently on that system is that you don't want to spread those contaminants to the most critical component areas. Bearings nowadays have very strict tolerances. Obviously, if you're flushing, you need to create custom jumper kits or jumper hoses to bypass the bearings. Obviously, the inlet and return lines on those bearings will be your points of target. And basically, in order to do so, yes, it can become difficult. You might have to have some expert pipe fitters, and really spaces might be a little tight. And there might be some areas in which you do not want oil to travel. And that's why you have blinds and jumper hoses. And you can also have measurement tools based on those jump kits. Those contaminants are measured in 100 mesh screens that are placed directly at those critical component points. So you can actually, during the flush and during that process, you can work your way down from dirtier screens to cleaner screens. So That's the major reason why we bypass bearings, is because they have strict tolerances, and you really don't want any of those contaminants to go into those critical components.
Okay, that's a good answer, and I love the fact that you answered. That was a question I was thinking about as well. So thank you for answering that. Greg, anything you want to add to that, or Jim?
I was going to say that you also need the high velocity. And so by jumpering the bearings, basically the velocities you're looking at are like 4 times nominal velocity or Reynolds number of 20,000. So the jump of that bearing helps improve that velocity. And the other thing that I know Robert knows is that we can put, they call them flushing blocks on the hydraulic system. So it's a way of flushing the hydraulic system. You basically pull off the servo valve and put a flushing block on. It's about the size of a deck of cards, and it allows for high velocities through the hydraulic system.
Nice. So
Yeah, that's an excellent point. I think one other additional item to keep in mind is a contributing factor when you're executing a flush. You have to have heat. A lot of other customers say, can we execute this basically shooting a high velocity of oil through the system? Really, the heat is the contributor. Really, the pipes start being receptive to the oil starts performing the way it's supposed to. And actually, a lot of that debris, along with that Reynolds number, making sure the inner pipe diameter is completely filled. There is a lot of key factors into it. That's why you really want to choose carefully on whom is going to be touching your equipment, how they're going to be touching it, go over a sequence of events, possible failures and critical component points in which you can assess whether it's a complete job. It's got to be from A to Z, making sure the most amount of pipes are flushed, and making sure that the other factor would be that your filter chambers are empty when you do so, because that's the other part of it, is when you're flushing, your filter chambers might start catching, if you have filters in there, some of those contaminants, and you really want those to be measured on a 100 mesh screen at the end of the day. Yeah.
Nice. Greg, are you adding anything to that, or?
No, I don't have anything else. That's perfect answer. I do have a question for Robert and Jim. So just getting back to confined space tank cleaning and your little lint-free rag collection of debris. What are the craziest things you have found in the bottom of a lube oil reservoir?
You have to think about that for a bit.
I found bird feathers, a lot of pens, and but you can see if you have your pen in your pocket and you're leaning over the top of the reservoir. It's sometimes cell phones, but yeah, we've seen all sorts of crazy things, I think, on
we find all kinds of items. Pens is very common. I think some tools that are perfectly intact. I mean, we recently did a flush out in the desert where we found a wrench that was there for about 20 plus years, perfectly intact, and the operator that was on site recognized that tool. There's a variety of items besides the bird feathers, besides RTB and other electricians work, because they're doing work on the top of the turbine deck possibly, and then a lot of that stuff just depending on how clean they are will drop into FME, and so there's a variety of items that are found.
Yeah.
And I guess it's not so exotic, but you'll see epoxy paint peel off. And so not exotic, but that's I see a lot of that.
Yeah, I think we found a grease gun once. An entire grease gun. The entire thing intact. I guess they're not going to be using that anymore. But a lot of things happen during these turnarounds. So I think if you're going into a turnaround, know that there are going to be changes. There are going to be crazy calls. Just prepare yourself for what happens.
Here's one thing to throw out too is some people on those turnarounds, crazy things, all that kind of stuff, is they take a shortcut and they'll use silicone as a gasket material. as opposed to what they're supposed to be using. And then that silicon makes its way into the oil and then plugs filters. And so silicon definitely is a big no-no, but I understand why people do it because they can't get the right gasket.
Agreed. And we actually had a question from Ahmed to you, Jim. He asked about the mobile system cleaner flush. Is it different for different OEM turbines, or is it one only which you can apply to all of the different OEMs?
So we really recommend this primarily in the only when needed, let's say. And so for years, this was the only hammer we had. But now we've got, they say when all you have is a hammer, everything looks like a nail.
Yes.
So that's where we were for years. We would always just mobile system cleaner, and the one. So it's very good when needed. And there's a lot of times when it's not, that level of cleaning isn't needed, because the big negative on it will hurt the demulsibility of the following charge. So we try not to, especially in steam turbines where demulsibility is of a key characteristic, we try not to have to use that mobile system cleaner. But sometimes there are times where that system is so fouled that we're convinced that a mobile solvencer isn't going to get the job done, and the customer knows that, okay, I am willing to sacrifice the emulsibility. We do feel comfortable that if we get the mobile system cleaner down to a 0.1%, so it goes in at, let's say, 7%, you've got to get it down to 0.1%. So that's a very, very thorough displacement flush. And if you do that, then you're going to be in good shape. But the trick is, you may have plans and you think you can get to 0.1%. And at the end of the day, I mentioned like the 19 point low point drains, maybe there was 21 and we missed some spots. And now we've hurt ourselves. So anyway, I would say by and large, the mobile system cleaner is good on gas turbines. The other thing is, you don't want to run continuously with it. Kind of like our chart here shows. We don't want to use that mobile system cleaner under operation. It's going to oxidize the oil prematurely. It's going to cause additional deposits later. It's going to hurt foam and demulsibility. So you put that good cleaner in there, but then you've got to get it out. And then that's the beauty of the solvencer is, hey, even if you've got some residual, maybe it's actually a benefit to you.
Okay, that makes sense. I like that train of thought, because I think a lot of times people struggle with going back to the question, what do we use and how do we use it? So great insight there in terms of getting it from 7 to 0.1%. Like that's a lot of things we need to do before you get there. So I'm just, I know we have at least 15 minutes left in our panel. Any questions that you all have for these experts on, preparing a system for any sort of turnarounds, please drop them in the chat. We will try and get to them. But I know a lot of times when we're getting ready for these turnarounds, one of the questions that we get asked a lot is that, how do you know that your oil is ready to be changed? Like, do you allow your oil to go on to the next turnaround? Can it last that long? What can you do in that situation?
Let's see, I'm just wondering if I think there's I think this is probably the best slide that Jim put together on that.
What are your limits involved?
Yeah. I'll kind of start it again. Remember all those 7 criteria, and then you're deciding, okay, where do we think we are, and can we? So in the oil business, we're always very proud of our oils, and we always think, and I'm always trying to talk customers into, hey, I think you got another 30,000 hours on this oil. But they're saying, look, I need reliability, and we have proof of performance. They're like, I can't do this for your benefit so you can have a higher proof of performance, because if I have a trip, that's $100,000, or in our especially in our own plants, in our refineries, we're talking $1 million a day. And so they are very conservative. And so you'd certainly, from the oil side and also just kind of the sustainability side, we like the idea of getting as long a service as possible. But at the end of the day, the customer says, look, reliability is number one.
Mhm.
So with all that in effect, then you look at these tests, you look at all the other criteria, and you make a decision. Hey, can I make it another 18 months, another 24 months? And that really dictates, whether you're going to change or not. Or other ideas, bleed and feed, pull some out, put some in. Those kind of ideas can be generated.
Yeah, I would agree. I also think there are case studies, obviously, on a lot of the items that Jim and Greg are presenting on. The solvencers, the additives, the items that are being presented obviously have been through thorough tests, and direct applicable knowledge can be passed down on various case studies, whether it's a GE turbine, whether it's another application in a different machinery. I would lean on the experts. I would lean on the data to actually help you make the best decision. Obviously, the starting point for me would be the oil analysis, and it's got to be comprehensive. Like Jim stated, it can't just be based on viscosity or on your base stock, but your wear metals, the ad pack, the type of oil, and the stress that you're putting on that oil will also determine a lot. The operating temperature and the ranges. I've noticed a big trend in varnish recently, and that is because a lot of the cooler applications on a lot of these turbines and a lot of these systems are not keeping up with the temperature regulation. So obviously your oil is working hotter, it's working harder than it's ever had in the past, all because someone has designed a new cool state-of-the-art cooler system, but that cooler is having trouble keeping up. So those are all contributing factors, but I would, when making a tough decision, you really want to surround yourself with facts, with data. And that's going to help you kind of put yourself in a successful position. Because otherwise, you're going to be having a shutdown pretty quickly, and it's going to be unexpected, and it's because of a particular reason. Yeah.
Oh, yeah, definitely. Anything you want to add to that, Greg?
Well, I want to bring up just one point that Robert brought up at the beginning of this. And, I think one thing that if you go through all your oil analysis and your antioxidants are still healthy, it looks like you have longer life in your oil, but you have a high varnish potential. Operationally, you've seen no issues with varnish whatsoever. One of the points that Robert brought up was what happens to that oil during the outage. So you may have an oil that you've decided still has extended life, and you're going to keep it in there during the outage. And so if you're out for a couple of weeks and now this oil has cooled down to room temperature or to ambient temperature, all of these deposits that are in the oil, they may have been in solution while you're operating, and now they've all come out of solution. So when you come back online now, your valves may be sticking. You may have a whole host of issues that you didn't have, when you were operating prior to the outage. So I think I just wanted to bring up Robert's point, considering what's going to happen actually when you bring the system down to the oil. Even if you're not doing an oil change, I think that's a really important point. And we've been talking a lot about turbo machineries, but this is even more relevant for other applications. If you look at some heat transfer systems, if you bring a heat transfer system down, you may never get it going again. You may literally have to look at removing pipes to get some of the deposits out of the system again. And so putting in a lot of thought into actually, if you're not doing an oil change, what's actually going to happen to the oil while it's hanging out during the outage time at ambient temperature.
Good point. Very good point. And I just I have two quick questions. One from Patrick, and he's asking about, have you had success with removing varnish from coolers with the MS Cleaner Flush?
Yes, but oftentimes, as Greg was pointing out, Robert too, is when the oil gets cold and the products of oxidation come out of solution and really bind to the tubes. Sometimes you give it a shot with a cleaner and see how well it does, and then it's very easy to tell because you got delta T changing temperature and delta P, so if you've done a good job or not. And so sometimes you give it a shot with the mobile, and again, the mobile system cleaner is more aggressive. So you give it a shot. We have been successful, but there's been times where it was so foul that wasn't going to get the job done. And now you're into the mechanical where you're kind of using a drill type device to actually etch out the deposits in a manual basis.
Oh boy, that does not sound very pretty. But moving on, we have another question from.
I just put a slide up that I don't think it's sharing on the screen. Are you able to?
Hang on. Let me get.
There we go. I just wanted to show this just for a moment that there are, in fact, we do have some cases where we've added mobile solvencer to a system. In this case, we don't have a lot of customers that put a dirty heater cooler bundle back into the oil typically, but in this case, this was a compressor and they had a chance actually they wanted to measure what will mobile solvencer do, and so this is kind of before and 30 days after having mobile solvencer in the product. You could see these, as Jim said, this is not pristine shiny metal, but a lot of the deposits have been removed. So I just wanted to make the point that it can be successful at removing some of these deposits.
That's a really good slide. Picture says 1,000 words. But jumping into this comment from Thanaraj, who is joining us from Singapore, so it is almost 1 a.m. on his side. What is the main flushing fluid used? It's a bit of a loaded question. So let's start with that part first. What is the main flushing fluid used?
I'll offer just that we always recommend the same quality of the final fill oil. So that's where you start. Certain OEMs are adamant about that. It must be, in particular, like MHI says you cannot use anything other than the same quality of the final fill product. And that's all well and good. And that's kind of your optimum recommendation. But customers will look at the budget side of things, the economic side of things. They say, okay, could I go with something less expensive? And the answer is yes. And then there's a different ideas. And so you could go with like a pure base oil. And then so we have products that we sell that are actually pure base oil. It's our heat transfer oils. We have a product like Mobile Therm 603 that is just a pure base oil, or other suppliers have just pure base oils. But that is a way to go to reduce your cost, is to use a pure base oil. We don't like certain. We know that when two oils come together, there can be an additive interaction, especially with the antioxidants, and they can fight each other. So we get very nervous, and as long as we understand, okay, this oil and this oil, and they're well known, no issues. But sometimes another oil meeting up with the final fill oil can be problematic on the final charge.
I'm just jumping into Robert and Greg. Anything you all want to add to that before I move to the other questions in the comments?
Yeah, I would agree with Jim 100%. Really, the rule of thumb would be to use the exact existing oil that is projected for that application. Now, if it's for a fiscal reason that you want to water it down a bit and use more of a base oil, 100% okay, and it is satisfactory to do so. Keep in mind when doing a flush, the overall purpose is to really clean up that oil at the same time. You have heat, you have velocity, and you also have filtration. The cleaner the oil is, running into that system and cleaning the pipes and all the important areas, and then collecting that measurement tool at the end, it's really going to be vital. So honestly, yeah, it'd be great to use the existing oil or a sacrificial oil and then throw that out and then get to your new fill and try to really drop isocode significantly on the initial fill of the new oil. it's going to help it give it a head start when starting up.
All right. Anything from you, Greg?
Well, I'll just point out, hey, Jim.
I seem to have gone sideways on you.
I'll just point out in other parts of the world, we have heard about some crazy things that are used for flushing. And maybe the craziest flushing medium I've heard is diesel fuel, used as a flushing medium for flushing out, turbines. And I would discourage that. I
Yes,
would say, please
highly.
stick with what Jim and Robert have said.
Definitely. And Raj is actually getting into what is the temperature and pressure used. I feel like this varies per system, but I'm leaving it to the experts on that. Anybody want to tackle that part of the question?
Sure. It really depends on the machinery and equipment that you're flushing. There is an OEM spec, and then also in most cases, the manufacturer has a determined target that needs to be adhered to very stringently upon the flushing stages. There are a couple areas where the oil is going to keep up with any temperature you're going to throw at it. Normal ranges for any temperature for a flush would range anywhere from 120 degrees to maybe exceeding 150 degrees. The pressures also are really determined on the equipment being used and the pipes that are being flushed. Obviously, in bigger applications where you're flushing a big steam turbine, obviously you might have differential pressure on some of the equipment being used, and that's a good measurement tool. But the PSIs usually will not exceed, depending on the application, 120 PSI. But there is an optimum range on the equipment that you're using to flush to actually give you a good parameter in which to stick to. And also, when you see those high PSI ranges, obviously they're for reasons. They're for specific reasons. You're catching specific contaminants that are causing a drag on the oil being flushed through the system. So that's something you really want to pay attention to, even when commissioning the unit back up and actually placing new filters into your unit and actually getting on turning gear or actually operating. You really want to listen to your system. You want to lean on your operators that have been on that unit every single day, day in and day out. See if there's adverse change, if there's something that is abnormal, because usually in most cases, if they identify it, they'll identify it very quickly,
Mm-hmm. Always use your boots on the ground. They are the ones that are around the equipment the most. I just want to jump into one more question because I know we have 3 minutes remaining. It's coming in from Peter, and he's asking when solvents is used for long-term deposit control, how does the oil behave when it's cooled down during the outage, with respect to keeping the varnish in solution? So I'm going to drop that in. Greg, what are your thoughts on that one?
Sure. So, one simple analogy for thinking about how mobile solvents impact the oil. It's like the oil has a natural bucket to hold things. A Group 1 oil has a slightly larger bucket than maybe a Group 2 oil. If you add mobile solvents, or now you have this huge bucket and can hold all sorts of degradation products. That's why you see the MPC number dropping quickly when the oil's cooled. Traditionally, you would see these things coming out of solution. Mobile solvents will keep them in solution. So as a result, you'll see a lower MPC value. But even more importantly, during an outage, you won't see these deposits coming out of solution.
That's
Great
very
question,
good.
Peter.
Jumping to Jim, anything you want to add to that?
Yeah, just like the size of the unit, like again, like a GE Frame 7 FA holds 6,200 gallons. So now you've got 6,200 gallons to hold all those deposits. And the deposits that we'll see, like in a last chance filter or in a servo valve, they're small. I mean, it's less than in a handful. So that is put back in the solution, and then when that oil cools, that's the beauty of it, because it is a base stock. So it helps hold those products of oxidations in solution even when you cool it.
All right. Anything you want to add to that, Robert?
No, I think you guys have it covered pretty well.
I just have one more very quick question from Raj again. He's wanting to find out how many times is it required to flush a system? And I think that highly depends on the system and what you have going on inside of it. But I'm leaving it to you all. Jim, we're putting you on the spot, starting off with you.
You're right. It's answering those 7 questions in the beginning helps dictate this. But if you do it right, it's once.
Okay, good.
And I think if you have a flushing business like Robert, it's many, many, many times.
Well, you're right. It is nice to be pretty busy. I think a lot of our business model is based on relationships. Honestly, we've had multiple referrals, and it's a lot by word of mouth. But honestly, it's based on the success rate. So if you do a flush correctly, yes, once is the optimum target. You're hoping that the customer doesn't have to incur that same situation in the near future. But at the same time, you want to make sure that it is strategically and fiscally responsible to execute those things, because these things are invasive. You got to make sure you have the right personnel on your equipment, because they can adversely really change when your system goes back up into operation. Adversely, all those changes, the flanges, the attention to detail, and all the pipe commissioning back up could have a very adverse effect on the actual system. So obviously the answer would be based on the data. When the data tells you that you actually need a flush, there's a lot of systems that actually tend to have a lot of scoring on the bearings. And that happens very frequently because nowadays our PM intervals are being extended. We're asking our pieces of equipment to run harder and produce more power than they have in the past. And it could be for a variety of factors. Maybe the parent company does not want to shut down. Maybe they want to extend the interval, which obviously in any maintenance strategy, it's going to affect your equipment that much more. So it really just depends on the data you're gathering between the oil analysis, your PM schedules, the sequence of events when doing your PM schedules and your confined space tank cleanings. Those are the things that are going to contribute to helping you make that decision.
All right, I think very well answered. Just a quick question. I know Greg already answered this in the chat as we're closing off. Thanraj is asking if mobile solvents is compatible with mixed lubricants, groups 1, 2, 3, and 4. I'm thinking that's 3. Yeah. So I'm
The easy
gonna.
answer is yes.
Yeah.
The more complex answer is that our experience is really on non-detergent based formulations. So we don't have a lot of experience putting this, say, in engine oils, so I would say I'd probably feel a little more comfortable doing some more work on detergent-based formulations first. But in non-detergent-based formulations, group 1, 2, 3, and 4 is all compatible.
All right. Anything from you with that, Jim?
No, but Greg and I are talking about working on engine oils as well too. So that's future
very
work.
Interesting. Very interesting.
Next panel to be.
Next panel, yeah, next LRVS. But we're coming to the end of the session. Well, but 3 minutes over time. But thank you all so much for sharing your knowledge with us. And I know our LRVSs, that's a tongue twister. Our LRVSs always join us in from all different parts of the world. I know Thanraj is coming in from Singapore and it's 1 a.m. on his side. So thank you for staying up. So with us, and we have on the other side of the world going back all the way back to the Americas. So I want to thank you all so much for being with us and sharing your knowledge. Jim, a lot of information that we learned from you. Robert, very good information, and Greg, I always love talking to you. So that's always a pleasure. So we are going to be getting ready for our next LRVS. I believe it's for the APAC region. So, look out for things that are coming, things that are going to happen soon. But thank you all so much for joining us. The recordings are going to be available online. It's already up on YouTube and LinkedIn. And we will be reaching out to you with more information. So stay tuned for our next LRVS. And thank you all so much for taking the time out of your day in all the different parts of the world just to have these sessions with us. All right. Thank you all so much. Bye.
Thank you.
Bye.
Thanks so much. Bye-bye.
Thank you.